uncertainty for the mass values. So now, what do we know for nuclear masses? Here is the plot for, from the atomic mass evaluation, which is a reliable database for nuclear masses. So it's the most recent one published in March this year. This is a chart of the nuclides. So here each block is one nucleus with the number of neutrons and protons. Here different color here shows how well we know about their masses. And the red color means we don't measure their mass experimentally yet. It has been predicted that maybe 7,000 to 9,000 nuclides could exist. But we have only discovered in laboratory for around 3,400 nuclides yet. And among them, only 2,550 nuclides have their mass measured experimentally. So as we can see here, there are still a lot of things needed to be done in future for mass measurement. And here I zoom this nuclide up. So this is arsenic 65. There are 33 protons and 32 neutrons. And the half-life of this nuclide is 170 milliseconds. So the half-life is very short. And the mass uncertainty for it is 80 keV. Here, this is the unit for energy, also for mass. So the relative uncertainty we know for the mass of this nuclide is 1.4 times 10 to -6. It's already quite good, but not good enough to study some very fine physics. So there are a lot of things to do. So around the world, there are many research groups dedicated to mass measurement for short-lived nuclides. And nowadays, there are mainly 4 different methods for mass measurement of short-lived nuclides. Here is a penny trap, and here is the MRTOF. Here is the storage ring and the beamline. So on the left side, we have these 2 kinds of methods which can accept low energy short-lived nuclide. And on the right side, we have the beamline and the storage rings which can accept high energy radioactive ion beams. So in general, by using the storage ring, the IMS based on storage ring, we have very short measurement time, so it's very suitable for short-lived nuclides. And the precision is quite good, and also we can measure a lot of nuclides in the same time. So earlier this year, we have published one review paper in the progress for the mass of exotic nuclides in this journal. So we listed different methods for mass measurement and for their applications. If you are interested, you can just refer to this review paper. Then how do we measure nuclear masses here in our lab? What we are interested in are short-lived nuclides. They don't exist in nature, so we have to produce them in the lab at first. Then we use some stable nuclides as the primary beam. We accelerate them to use this synchrotron up to some usually to 400 MeV per nucleon. And then they extract the beams to hit a production target. at the entrance of this rubber tube beamline. And then they are the fragments, which includes some the nuclides of interest into this experimental storage room. And here we have a time of flight detector. There is a very thin carbon foil in the top detector. Every time when the ion passes through the carbon foil, it might produce some signal. And then we recorded all of this signal by using an oscilloscope. Then from these signals, we can extract the revolution times of these ions, which is how long time does it take for this ion to circulate for one turn in the ring. Then from the revolution times, they can extract the mass to charge ratio, then they can go to the mass. That's the basic idea for how do we measure that. But here we have this so-called isochronous mass spectrometry. Why do we need that? Because the ions are stored in this ring have some large momentum distribution. And so for one specific ion species, the faster ions move on a longer orbit, and the slower ions circulate in a shorter orbit. And as a result, the final revolution time does not depend on the velocity if the so-called isochronous condition is fulfilled. So gamma is the Lorentz factor of this ion, and gamma T is a setting parameter for the ring. So when gamma equals gamma T, we can see that the ions fulfill the isochronous condition, and so we can extract the mass directly from the revolution time. Then we have the spectrum of the revolution times. Here, each peak corresponds to one or more ions. For example, for this one, we have the copper 52 in its ground state, and also in the isomeric state, which is long-lived excited states. So the excitation energy is only something like less than 400 keV. And so we can resolve them clearly. It shows we have very high mass revolution. Then from the revolution time, by using the masses of some well-known nuclides as references, we can establish the relationship between the revolution time and the mass to charge ratio, and then we can get the masses. So what we have done up to now, this is the nuclear chart showing what we have measured all of these years. We started our program on mass measurement in 2007. We performed the first test experiment in December 2007, and the first experiment in 2009. And so the first results were published in 2011 here. And then later, roughly each year, we have one experiment, and we measured these masses and published these results. So by using these mass values, we have studied some physics, such as for nuclear structure. Here we have seen one isomeric state in iodine 101, and some decay of this isomeric state. And also we studied some isospin symmetry in nuclides by using these masses. And for this neutral-rich side, we measure the nuclides of this Scandium 54, for example, and studied the shell evolution for nuclear structure. And also, our results were used to study RP process that's important in nuclear astrophysics. I will say more about this story here. The X-ray burst occurred quite frequently in the universe, and so it occurs on the surface of a neutron star, which attracting some material from a companion star in the stellar binary system. So the material attracted on this neutron star is rich in hydrogen and helium. So then some runaway nuclear reactions could happen there, which shows as X-ray bursts. So the epi process is the process powers the X-ray burst. RP is for the rapid proton. So the nuclides capture protons and then beta decay back to the stability line and then come to something here. It's very important to have some nuclear parameter inputs to study these X-ray bursts. For example, here some waiting points are predicted, but the reaction rates of them depends exponentially on the energy, the reaction energy, which is also related to the nuclear mass. One question is that is germanium 64 usually a waiting point here? It shows as a red dot here. So if it's a strong waiting point, it could influence the light curve and the final abundance, the final components of the ashes in the burst, and also the reaction path. So if the germanium cannot go very fast upwards by proton capture, it has to wait for a long time. For the half-life, for the beta decay for this nuclide is very long. It's something like 60 seconds. It's long compared to the burst time. But how long does it wait depends on how tight this nuclide can capture one proton. Then it depends on the mass of arsenic 635. It's not easy to measure this mass because the production rate is very low and the half-life is very short. They managed to measure its life, its mass for the first time, and by using our mass values, they can calculate the light curve and the abundance of the final components in the burst ashes. So the conclusion in our result is germanium 64 is not a significant RP process waiting point. This is our first important results in this storage ring. And we are happy that Professor Phil Walker at the Surrey University, England, wrote an article in nuclear physics to introduce our work. The title of that article is said, Starbursts Pinned Down. So it says that one of the main uncertainties in the buildup of X-ray bursts from neutron stars has been removed with the weighing of a key nucleus. arsenic 635 at a new iron storage ring. So up to now, it seems very nice. The problem has been settled, but it's not the end of this story. We still remember this plot, and we measured the mass of arsenic 635, but selenium 66 is also very important for this study. And Hendrik Schatz from the MSU United States later published an article on nuclear masses in astrophysics. Well, for the masses for the RP process, they said that the remaining unknown masses defining the critical Q values are merely selenium 66 and so on. So later, they also have some detailed calculation showing that the mass uncertainty for arsenic 65 has to be improved, and also the mass for selenium 66 is important for further study. So also they have done some similar calculation, and the conclusion is similar. They need to measure the mass of selenium 66. It's not easy to measure arsenic 65, and it's even more difficult to measure selenium 66. But anyway, we managed to perform the experiment earlier this year, in January this year. So this is the preliminary results about the revolution times. You can see many peaks that's for different ions produced in this experiment. And we have produced more than 100 nuclides, different nuclides in this experiment. Then, but here for further, the data is still, the data analysis is still under progress. I show you some preliminary results for particle identification here. We need also the charge resolution. For some of the nuclides have very similar mass to charge ratio, and so their revolution times are very similar to each other. Here is one example for cobalt 51 and argon 34. The mass number to the charge number is the same, and the revolution time is similar. So we have to develop some methods for particle identification. And recently we improved this method, and this published as a cover paper earlier this year. And also by using this parameter for charge for particle identification, we can see we identified selenium 66, crypto 70, and so on, many nuclides. Here, the X-ray, this is for the revolution time, and here is the parameter for the charge, nuclear charge. You don't need to know the details. So when it seems I am running out the time, so I skip some of the next slides. So in this experiment, we used a new schema for mass measurement. Previously, we have only one time-of-flight detector. Then we can only measure the revolution times of the ions stored in the ring. But now we have two time-of-flight detectors installed at a straight section in the ring. Then we can measure also the orbital length. From that, we have better mass resolution and so on. I skip some slides for the summary and perspective. So we have some new facility is under construction. This is a photo for this construction side for the high intensity heavy ion accelerator facility. So we will have higher beam intensity and in future. And this new project is located here, not far from Hong Kong. And so this is the summary. We measured some mass and we will measure some more masses. We are developing a double top IMS technique. And so the future facility half is being constructed. This is our collaborators for mass measurement, and I thank you for your attention. Thank you.
Dear Wang, thank you for your excellent presentation. With your sanction, I would like to ask, is there any question? Next presentation belongs to Hakan Erkol. He will talk about multimodality imaging techniques in medical physics.
Hello.
Hello.
My screen. Okay, I think you can see. You can hear me, right?
Yes, we can hear.
Okay. First of all, I would like to say that I am very grateful and honored to give this opportunity. Good morning. My name is Hakan Erkol. I am from the Department of Physics in Boğaziçi University. Today, I will talk about the multimodality imaging in medical physics. Here you see my outline. In the introduction part, I will talk about the medical imaging techniques, and then I will explain the phenomena behind the light interaction with tissue. After the introduction, I will mention the physical modeling of the photon transport and heat propagation within tissue. I am going to present an analytical physical model to describe not only the photon propagation, but also heat transport in tissue. I am going to validate our results by performing numerical and magnetic resonance imaging experiments. In the application section, I will talk about one of the potential applications of our physical method, which is the thermal ablation therapy. And then I am going to introduce a novel imaging modality, which is called photomagnetic imaging. It has been developed by Gültekin Gülşen and his group in University of California, Irvine. And then I will talk about the limitations of the standard image reconstruction algorithm used in photomagnetic imaging. And I am going to present a novel hybrid algorithm based on our physical model. And I am going to conclude my talk with the impact of our study on the machine therapy and algorithm techniques. The medical imaging can pretty much be divided into two main categories based on its sensitivity. These are anatomical and functional role molecular imaging techniques. Magnetic resonance imaging, ultrasound, and computed tomography are used for anatomical imaging, and they provide structural information with the high spatial resolution inside tissue. Optical and nuclear imaging techniques provide in vivo information on a cellular and molecular level. One of the main advantages of the optical imaging is that it is safe for tissue because it utilizes a non-ionizing radiation mechanism. Unfortunately, it lacks the high spatial resolution as opposite to nuclear imaging techniques. As light propagates within tissue, it interacts in two ways, namely absorption and scattering. They are both wavelength dependent and they are very low in the near infrared region. Absorption coefficient represented by mu is defined as the probability of light being absorbed per unit length. Absorption occurs due to the interaction of light with tissue chromophores. The main chromophores are hemoglobin, oxyhemoglobin, lipid, and water. Scattering is resulted from the refractive index mismatches at the microscopic boundaries, such as cell membranes. Scattering coefficient represented by mu s prime is defined as the probability of light being scattered per unit length. tissue is highly diffusive, so that photons cannot travel in a straight line, but they change their directions when they encounter scattering particles. The region from around 650 and 1000 nanometer is called therapeutic window or optical window. In this region, many imaging modalities have taken advantage of the fact that both absorption and scattering are very low.
Here I'll call.
Yes.
We don't see other slides.
Really? Okay.
We can see only first slides.
Oh, really? I am sorry then, but I can see, I don't know.
You have to start PowerPoint.
Okay, thank you very much.
You have to start it.
Okay. What about now? Can you see?
Yes.
Okay, okay then. Now I am on slide. That will be very quick. 4. I think you can see now, right?
Yes, we
Okay,
can see.
okay. Sorry about that. I couldn't realize. I will continue then. I was talking about the interaction of light with biological tissue. We have actually absorption and scattering coefficients. I already defined them. And here it's important to note that here both absorption and scattering are very low in the infrared region, and many imaging modalities have using this fact. Thus, this allows for the photons to travel deep into tissue. The goal of the optical imaging to obtain three-dimensional maps of the optical properties within medium, namely absorption and scattering coefficients. Absorption map can be used to obtain chromophore concentration, and chromophore concentration may yield clinically important information. As you can see, these following three maps, tumor cancers have higher hemoglobin concentration, lower oxygen saturation, and higher water content compared to healthy tissue. Here, it's also important to note that the absorption coefficient depends on the wavelength-dependent extinction coefficient and chromophore concentration. Okay, first of all, we need to model the light, and the light propagation within tissue can be modeled by using the radiative transfer equation. The radiative transfer equation is an integral differential equation which is given by the following expression. But it is very hard to solve and very time consuming, so that we need a simple model. Now we are going to utilize the photon diffusion approximation based on these two assumptions. The first one is that the scattering coefficient is much greater than the absorption in the near infrared region, and the light source is also isotropic, which means after traveled by a distance of mean free path length, the probability of light moving in any direction is the same. Based on these two assumptions, we have the following photon diffusion equation. The left-hand side, the first term on the left-hand side represents the temporal variation. The second term describes the scattering photons. The last term on the left-hand side describes the loss of photons because of the absorption. And we represent the light source by S, which is on the right-hand side of the equation, which is the source term. We can solve the diffusion equation either numerically or analytically. If the medium is heterogeneous and the shape is irregular, then we cannot use analytical approaches. We need to use numerical ones. In optical imaging, the finite element, finite difference, and Monte Carlo methods are widely used. On the other hand, if the medium is regular and then it is homogeneous, we can implement analytical approaches, for example, Green's function methods, integral transformations such as Laplace or Fourier transform. In diffuse optical imaging, we prefer to use the finite element method in our calculations. Let me summarize the finite element method very quickly. The medium is discretized into very small elements. In our calculations, each element is triangular, and the total solution consists in basis functions. These basis functions join at some points. These points are called nodes. Actually, the diffusion equation is linearized and written in the following matrix form. This matrix is called system matrix. The optical properties is also written in the matrix forms so that the following matrix equation is solved. This can be very time consuming, dependent on the number of meshes. Now let's talk about solving the diffusion equation analytically. Actually, we are going to solve the time-independent diffusion equation. I will explain why. We have the following assumptions. First of all, we neglect the temporal variation term because we are going to use a continuous wave laser. And then we also assume the diffusion coefficient D is uniform or constant, and we are going to model the light source by the Dirac delta function. Here, gamma is the strength of the Dirac delta function. Based on these assumptions, we obtain the time-independent or continuous wave photon diffusion equation. And then we solve this equation in two-dimensional polar coordinates. We obtain the solution as a combination of the Bessel functions of the first and the second kinds and sinusoidal functions. We place the light source along the x-axis to take the advantage of the symmetry of the system so that we set differentiation constant dm0. Here we are going to introduce our integral-based Green's function approach. We solve the diffusion equation within the medium, except that at the source position. We are going to divide the medium into two subregions. Here you see the first one, and the other one is the region between the source and the tissue boundary. We implemented the following boundary condition, which is the Robin boundary condition. It is mainly used for tissue imaging. It relates the photon density to the flux, photon flux. Here eta is a constant, taking into consideration the refractive mismatch in the index between the boundary and its environment of the tissue. And by implementing the properties of the Dirac delta function, we obtain the following differentiation constants A, B, and C. We have an infinite summation, but after some order, the contributions coming from high orders can be negligible. We take the first 50 solutions. It is more than enough to obtain an accurate result. We validate our results analytically. For the following optical properties, we solve the diffusion equation by implementing our physical model, and we obtain the two-dimensional photon density map. As we see, the photon density has the maximum value at the source position, and it decreases with the distance from the light source as expected. We also present our results in this profile, and we see that our results are matching very well with the results obtained by the finite element method, except that at the source position, our results are a little bit higher than the numerical ones. This is resulted from the interpolation problem in the finite element method. We also extend our method to the three-dimensional case. In medical imaging, in some cases, the mouse, cross-section of the mouse can be approximated by a cylindrical volume. And we add another dimension along the central axis of the cylinder. We have z coordinate. By implementing the Robin boundary condition for the radial coordinate and Dirichlet boundary conditions for the top and the bottom surfaces, we obtain the differentiation constants A and B so that we express our photon density within the medium at every point. Here, we are going to validate our results by the three-dimensional finite element method calculations. The medium is illuminated by a laser source, as you can see from the schematic of our problem. We use light source S, and 16 detectors are equispatially placed around the tissue boundary. And we solve the diffusion equation at every detector point for 3 different axial positions. In other words, for 3 different z values. And we present our results in this logarithmic scale figure because of the dynamic range of the results, which means the photon density or photon flux is very sensitive to the distance from the source position. Line shows our analytical results, while marker represents the numerical ones obtained by the finite element method, and they are matching very well. Let me summarize our new method. First of all, it yields very detailed photon density or photon flux expression, and it allows for the implementation of any realistic or complicated boundary condition. It decreases the computational time, which is very important, especially for the image reconstruction algorithm. Another way of interaction of light with tissue is the increase in temperature resulted from the laser heating. Here, the medium is illuminated by a laser source. Here we have an inclusion, as you will see now. The medium is illuminated by a continuous wave laser, and here we have inclusion. I think you can see that the increase in the inclusion is higher than the increase in the background because of the higher optical absorption in that inclusion. More photons are absorbed in that region, in that inclusion. As a result of this, we have more heat. The photon density is converted into the heat, and the change in the temperature is proportional to photon density and the absorption coefficient. We are going to model the heat propagation within tissue by the following two differential equations. The first one is the photon diffusion, and the other one is the Pen's bioheat transfer equations. In the heat equation, we ignore the perfusion rate and the metabolic heat generation for our calculations. Actually, we are going to use the solution of the photon density in the solution, source term of the Pen's bioheat equation. Actually, this is the thermal energy resulted from the photon absorption. So that we are going to express the increase in temperature. We use the following boundary condition, which is the heat convection boundary condition. It relates the change in the temperature to the derivative of the temperature with respect to normal. H is the heat transfer coefficient. We actually already obtained the photon density solution. By writing this solution in the source term of the heat equation, we obtain the increase in temperature. Ts is the surrounding temperature. And here we have two infinite summations, but after some point, likewise the previous case, the contributions coming from high orders can be negligible. And then we take 100 solutions for each summation. And then we also validate our results by performing homogeneous phantom experiments. Phantoms are prepared in our lab in University of California, Irvine. And we mainly use agarose. We added the intralipid and indening to set the optical properties of the phantom. And we conducted an experimental study. Actually, we utilized the magnetic resonance thermometry system. The medium, in our case, the phantom, is illuminated by a near-infrared laser source. And the induced temperature is acquired by using MRT technique. Here you see our experimental setup. We have a laser which is connected to optical fiber wires in which the light travels, and it is collimated with the lens. After this collimation, it illuminates the phantom in the RF coil. Here you see the data acquisition diagram. Actually, before the laser is turned on, we have already a baseline scan. The laser is turned on. As a result of this, the temperature is increasing. And when the laser is off, the system cools down. Actually, in magnetic resonance thermometry, we are measuring phase difference between the heating phase and baseline phase by using the following relation. We are calculating the increase in temperature. We also validate our results experimentally. We obtain the temperature map by using magnetic resonance thermometry technique, and you will see the analytical and numerical temperature maps. We also present our results in the following profiles, and we obtain that they are matching very well. For a better comparison, we also express our results in the logarithmic scale temperature maps and logarithmic scale profiles. Below the noise level, here, dash line represents noise level. The experimental results start deviating from the computational ones. We also validate the temporal aspect of our method. We obtain the increase in temperature, 2 different points. The first one is away from the source position or boundary. In that case, the temperature is increasing linearly with time. If this position is very close to the source position or tissue boundary, this time the temperature is increasing exponentially with time because of the heat convection boundary condition. it saturates. We perform an ex vivo experiment on a chicken breast piece. Here you see that the chicken breast is depicted by this circle, and we obtain the experimental and analytical and numerical temperature maps. We present our results in both linear and logarithmic scale figures, and we saw that they are matching very well, except that below the noise level. It's around 0.1 centigrade degree. Let me summarize our view method. We presented a fast and accurate algorithm which decreases the computational time up to 20-fold. And even though our results are valid for the homogeneous case, still we can use them for the less heterogeneous cases, as in the example of the chicken breast experiment. Our method allows for the implementation of any complicated or realistic boundary condition. One of the potential applications of our method is the laser ablation therapy. It is used to burn cancerous tissue. It is minimally invasive and good alternative over the conventional surgery because it provides fast recovery times and the complication rates are very low. Here we need to determine two important factors, which are the magnitude and the duration of the increase in temperature. Actually, we can determine them by using our simulation studies prior to the experiment. Okay. I am going to introduce a novel medical imaging modality, which has been developed by Gültekin Gülşen and his group in University of California, Irvine. It is presented to increase the low spatial resolution of the optical imaging by utilizing the magnetic resonance thermometer. The phantom or medium in general is illuminated by a near-infrared laser source, and then induced temperature values are acquired by using the magnetic resonance thermometer. The photomagnetic imaging requires to solve a multi-physics problem, which we already mentioned, the photon transport and increase in temperature within tissue. Let me talk about the standard image reconstruction algorithm, which is mainly used in photomagnetic imaging. The phantom is illuminated by a laser source, and then the major temperature is acquired by using the magnetic resonance thermometry technique. At the same time, the forward problem, the combination of the photon diffusion and heat equations, is solved, and simulated temperature is obtained. If the error between the measured and the simulated temperatures is small enough, then the algorithm automatically stops. Otherwise, the absorption is modified and substituted into forward problem, and the forward problem is resolved. The new simulated temperature is obtained. The error between the measured and the new simulated temperature is recalculated. This continues until the error becomes very small. The first part of the problem is called the forward problem. In that problem, the simulated temperature is calculated from the optical and thermal properties within the medium. On the other hand, in the inverse problem, the optical absorption is obtained from the measured and simulated temperature values. The forward problem in photomagnetic imaging consists in solving the following photon diffusion and heat transfer equations. In the inverse problem, the absorption maps are obtained by minimizing the following objective function. Here, we are going to define the Jacobian. We are going to increase the absorption coefficient at a given node or given point in the medium. As a result of this absorption, the increase in temperature found, and then the change in the increase in temperature with respect to change in the optical absorption is defined as the Jacobian. But this can be very, actually not can be, it is very time consuming when we use the standard image reconstruction algorithm. For optical images with high spatial resolution, we need very fine meshes. And this leads to a considerable increase in the computational time, so that we need a very fast image reconstruction algorithm for the real-time imaging applications. Here we are going to introduce a novel analytical-based image reconstruction mechanisms to solve the forward and inverse problems. Actually, we already solved the forward problem. The solution of the inverse problem, unfortunately, is not possible analytically. Let me explain why. When we increase the optical absorption at a given node or given point, we make the whole medium heterogeneous. And for this heterogeneous case, we cannot solve the forward problem. As a result of this, we cannot solve the inverse problem either. And unfortunately, we cannot obtain the Jacobian analytically for this case. And we want to come up with a new idea to decrease the computational time for the real-time imaging applications. Here, actually, we are learning the standard photomagnetic imaging Jacobi. The medium is illuminated by a laser source and the temperature map is obtained. By changing the optical absorption at a given point, we obtain the Jacobian. And we can describe the Jacobian by a kernel. And the kernel consists in the amplitude and the shape of the Jacobian. We realized that the shape of the kernel is spatially invariant after the normalization, which means the kernel has the same shape at every point within the medium. We performed a lot of fitting series and we reached this fitting formula. We tried to validate our result, this fitting formula actually, and we obtained the maximum amplitudes of the Jacobians obtained by our methods, and with the ones obtained by the numerically by the finite element solver. And we saw them, they are identical. What about the amplitude of the kernel? We know that the shape of the kernel is spatially invariant. On the other hand, the amplitude of the kernel is decreasing with the distance from the source position. Now you can see this from figure D. It decreases with the distance from the laser source. Here, we are going to change, this is important, we are going to change the optical absorption at every point. Unlike the previous case, this time we are changing the optical absorption at every point within the medium so that we make the medium homogeneous with the new optical absorption. And we obtained the total Jacobian. We realized that, we found out that actually, this Jacobian actually is the sum of the individual Jacobians. And we write this in a pixel basis form. Actually, this is the definition of the convolution. By deconvolving the shape of the kernel from the total Jacobian, we obtain the amplitude of the kernel. As you can see, our results are in a very good agreement with the ones obtained by the standard finite element method algorithm. Let me summarize analytical photomagnetic imaging image reconstruction algorithm and the data acquisition timeline. For the initial optical and thermal properties, the forward problem is solved and the simulated temperature is obtained. And then, by implementing our method, we change the optical absorption at every point and we obtain the total Jacobian. At the same time, by using our fitting formula, we find the shape of the kernel. By deconvolving the shape of the kernel from the total Jacobian, we obtain the amplitude of the kernel, and then the product of the amplitude and the shape gives the analytical Jacobian. Now the experiment starts. The laser is turned on for 8 seconds and the major temperature is acquired. And we repeat it for other 8 seconds. And we use the major temperature obtained by MRT, the simulated and analytical temperature values by implementing our physical model, and we substitute them in the following expression for the updated optical absorption. Actually, we obtain the image. For the following optical and thermal properties, we also validate our results. We have 2 inclusions which have 4 times higher optical absorption coefficients than the background. The medium is illuminated by a laser source. The temperature map is not enough to recover the optical absorption. Here you see the optical absorption map, which is obtained by solving the inverse problem by the finite element method. But after the first iteration, still it's not enough to recover the optical absorption. Nevertheless, after the second iteration, the finite element method recovers very well the optical absorption. At the same time, we implement our method and we reconstructed the absorption map very well. And we compare our results with the ones obtained by the finite element method after the second iteration, and they are very close to each other. They are matching very well. Here, to obtain an image by using the FEM for one iteration, it takes approximately 30 minutes. But if we implement our analytical approach, the physical approach, we obtain pretty much the same image in just 7 seconds, which is very important for the real-time imaging applications. We also perform experiments on homogeneous phantoms with 2 inclusions. Again, we have the same optical properties. Here you see the temperature map, and then optical absorptions obtained by the finite element method after the first and the second iterations, respectively. And we also obtain the results analytically. We present our results in these profiles, and we saw that they are in a good agreement. Here you may see some artifacts. This is resulted from the modeling of light source by the Dirac delta function. Normally, it should be modeled by a Gaussian function. But overall, the approach gives accurate results. To conclude, the computational time was very long in optical imaging, and with this, our approach, we were able to decrease the computational time, and our method allows for the utilization of any realistic or complicated boundary condition. We developed a fast and efficient software for the laser ablation therapy applications. Another important problem about photomagnetic imaging was the very long computational time, which makes it very difficult for the real-time imaging applications. With our new method, we were able to decrease the computational time up to 500-fold. I would like to thank my collaborators in University of California, Irvine, Orhan Nalcıoğlu, Gültekin Gülşen, Faruk Noizi, Alex Tuk, and Tiffany Wong, from Boğaziçi University, Mehmet Burçin Ünlü, Nasir Oluç, and Boğaziçi University and University of California, Irvine. I would like to thank you for your participation.
Thank you for your presentation. Is there any question? No question. Now we move. There's a question. Please.
Thank you for your presentation. My question is about what's the difference range is okay while imaging techniques. For example, in first imaging techniques is we can get X and another one X plus 1. Is it okay while results, and what's the maximum range while that results?
Actually, we obtained normalized solutions, and then by using the strength of the laser, the photon, the number of photons, we fit the results. Actually, we are using the normalized profiles. The profile is important because we have some loss when photons are moving. That's why we are always using the normalized results.
Thanks a lot.
Thank you for your question.
There is no question. Thank you again for your presentation. Warm greetings from Bodrum. Now we move last presentation in this season. The presentation belongs to Orhan Öztürk. He talked about magnetic layer formation on a non-magnetic stainless steel substrate by nitrogen ion implantation.
Hi, everyone. Can you guys hear me?
Yes, we can hear.
Okay. Title of my talk, as you see, magnetic layer formation on a non-magnetic stainless steel by nitrogen ion implantation. My name is Orhan Öztürk. I'm from Izmir Institute of Technology, and this work has been performed by two of my students, Özgün Karataş and Refik Adal. By the way, I appreciate the invitation by the Turkish Physical Society Organizing Committee. Let me tell you about a bit about the material, stainless steel and nitrogen ion implantation. So my, okay, let me start. I made the same thing. Okay, now, okay. The main motivation, of course, we have this material. Most of you probably heard about the stainless steel. Of course, steel is basically a composition of like iron and carbon. What makes it stainless steel when you add chromium? So we have like stainless steel. In our case, like basically stainless steel is an iron chromium nickel alloy, such as like 304 stainless steels, 310 stainless steels. And of course, like as Turks, we like drinking Turkish tea and so on. Like most of the teaspoons, for example, if you look at behind, or spoons or knives, you see that behind is written like 1810. There, 18 is the amount of the chromium as weight percent or whatever, and 10 refers to the nickel content. Okay, so the other element is main element is iron. So the chrome in this alloy makes it corrosion resistant, and the nickel makes this material, its crystal structure, stable. So this alloy material, in this case, we study 316L stainless steel, which is a crystalline structure, face-centered cubic. Okay, so it's an important alloy. Of course, it's like widely used in industry. It's like such as food industry, or like here, as you see, in the case of like this type 316L, it's also used in dental applications, like orthopedic applications. This material has an excellent corrosion and oxidation resistance. That this is mainly due to the chromium oxide layer. As it is, this material at room temperature is non-magnetic. Here's the crystal structure. Here you could see face-centered cubic structure. These like elements, iron, chrome, nickel, they are like randomly distributed in the crystal structure. That means lattice is periodic, but there's no periodicity compositional. Okay. So now, what is the problem with this material? It's like it has a high corrosion resistance, oxidation resistance. Of course, like there are many applications in industry. These materials, they are like in contact. Okay, so our main motivation when they're in contact or in the body, they of course they have like some problems with the friction, with the wear. Also, for example, when they are used as dental implants and as orthopedic materials, there might be a problem of interaction with the surface of these materials in the body, with the body fluids. So there's this issue of metal ion release, such as like chrome, nickel, molybdenum, cobalt. So they might be kind of toxic. Also in terms of the long-term durability, we need to improve the surface properties of these materials. Okay, not the bulk, the surface. So to solve this? So when these materials when they are in contact with the body fluid or with different type of materials, there's this like friction wear problem and so on. So so what we do, we surface modify. Okay, we do a surface modification by various techniques. One of them is like, for example, ion implantation. You have like another technique, plasma nitriding. Another technique could be, for example, physical coating or different types of like PVD, CVD, and so on. So the idea is to improve the surface chemical and mechanical properties. Of course, in our case, what we do, we put nitrogen ions into the surface of these materials. So we create new structures, new phases in the surface layer, okay? So, of course, this has been a research for the last 20, 25 years in my case. And of course, ion implantation is a technology well known for, like, for example, in semiconductor technology for doping purposes. When we say like you dope an N-type material or P-type material, that's basically due by ion implantation, okay, to make PN junctions and so on. So, of course, there are different types of ion implantation techniques. In our case, we combine with our colleagues, of course, this is a collaboration work, combine high flux nitrogen plus thermal diffusion, okay? So this is like a cross-sectional view here, okay? So on top of our material, we have an oxide layer, but in our case, of course, oxide layer may present as a barrier to the nitrogen ion beam. But before the nitrogen ion implantation, what we do an argon. We use an argon ion beam to sputter remove this oxide layer so that this nitrogen beam can enter the material easily. Of course, we do this under certain implantation conditions. Here, the low energy, high flux nitrogen implantation system. This system, of course, is designed by our colleagues at Colorado State University in Colorado. Basically, of course, you know, this, I'm not going to go into the details, but we have to have an ion source, ion beam optics. For example, like we have an argon here. Argon we use for like sputtering conditions. So we have like nitrogen or different types of gas. We ionize them, then accelerate them with ion beam optics. We have the target material. Of course, we have to have a certain temperature. For example, in this case, we use these high flux beam conditions like 0.7 kilo electron volt ion beam energy, flux like 2.5. This is like corresponds to 10 to the 19 nitrogen atoms per square centimeter is quite high flux. And the substrate temperature we maintain around this 400 degrees C. Why? Because we want a certain specific phase to be formed in this 316 stainless steel surface, okay? Because if you go above this temperature, the chromium from the substrate material combines with the nitrogen, forms a chromium nitride phase. Although this phase is hard and it has important properties, but in terms of the corrosion resistance, which is not desirable. So these are like optimized implantation parameters, okay? We use implantation times of like half an hour, 90 minutes, and like 4 hours, okay? So substrate material, as I said, 316 type stainless steel. Substrate phase, we refer to as face-centered cubic gamma structure. And from the X-ray diffraction analysis, we find the substrate lattice constant to be 3.57, okay, with certain precision angstrom. And of course, this material that we are working on it is a polycrystalline material, okay, with grain size ranging from 20 to 50 microns, okay? So these are not single crystal materials, a polycrystalline material, okay? So in fact, when we implant nitrogen goes into these like different grains. So we have like grain size effects. It's kind of interesting, single grain effects and so on. Okay, now let me just, we have done some structural characterization, mainly X-ray diffraction. So we do X-ray diffraction or our high flux, low energy implanted stainless steel sample. Here's the substrate material, untreated, unimplanted, no nitrogen here. As you see these peaks, they refer to these gamma peaks like the 1-1 orientation, 2-0-0 orientation, substrate peaks. Here, you can see this a simple drawing model here, substrate. So we send the X-rays from the top here. You know, I don't want to go into the details of the XRD analysis, it's very standard. So now, when we implant the nitrogen, so we form this layer here, okay? These are the XRD, and so we have new peaks. You see the new peaks, they are shifted to the left, lower angles here, that which means lower D, higher lattice constant, okay? And from also, we could say from here that, okay, so this is the 1-1 orientation. You see this is the 2-0 orientation. As you see, almost no substrate peaks, okay? So that means X-rays quite penetrate. This is like from this analysis, just from the X-ray diffraction analysis, we could say that this top layer, new layer with the nitrogen, more than 5 micron thick, okay? We could estimate that using the linear mass absorption coefficients and so on. For example, if you look at the 4-hour implanted sample, you almost see no substrate. That means, okay, you could say like more than 5 micron thick implanted layer. Okay, this is a simple model here. So now from this analysis, we know that there's a new phase formed on the stainless steel substrate. We call this expanded austenite phase formation, which is designated as gamma 7 iron chrome nickel. That means nitrogen, basically in the FCC structure of this material, goes into the it goes interstitially into octahedral sites. Okay, so that means it goes into the FCC lattice, and there's this expansion of the lattice. So the lattice basically remains FCC, but of course this is a polycrystalline material. This not a uniform expansion and so on. And so on. Okay, so we could also, there are some like single grain effects, such as like preferential 1-0-0 orientation. Also, some nitrogen has a preferential diffusion in certain oriented grains. Okay, these are like single grain effects. That's kind of interesting. It's a polycrystalline material, but it has some interesting single grain effects. Anyway, let me also, we have done some composition analysis, secondary mass spectroscopy, electron microscopy, and so on. We have here compositional diffusion profiles for different samples here. You see from here, these are like the implanted layer has high nitrogen concentrations, like as high as 30 atomic percent, and the profiles, non-error functional and diffusion profiles. In the past, we have modeled these, or in literature, they've been modeled with different models. For example, concentration-dependent nitrogen diffusions. Okay. Here, of course, like also we have done some like cross-sectional analysis. Here we could see the layer expand, the layer thick nitrogen implant layer from here to the left and to the right, and we have an epoxy here, kind of like the profiles, SIMS. Okay, so here, of course, yeah, these are the of course, we also investigated hardness properties, micro hardness and nano hardness. Micro hardness were done on the surface of the implanted layer. Nano hardness measurements were done on the cross section of the layer, and there's a clear increase in the hardness of these implanted layers. And from the cross section analysis, we could see that this expanded layer here on the right hand side, kind of like you see more than 5 micron thick. It also shows that this is good corrosion properties and so on. Of course, these structural and mechanical properties are our main motivation, but we realize that this phase also, this layer, this nitrogen implanted layer on this stainless steel material has magnetic properties. Okay, so basically this new phase on the stainless steel substrate becomes ferromagnetic, and this ferromagnetic expanded phase basically linked to large lattice expansions as high as 10%, and now this is due to the high nitrogen contents. Okay, nitrogen content in the implanted layer reaches like as high as 30 atomic percent. Of course, this entire layer is not ferromagnetic. Also, there is like paramagnetic phase here, which is of course for nitrogen contents 20 atomic percent or less. Okay, as I said earlier, substrate phase original material is paramagnetic. Okay, so why this layer or with high nitrogen, high expansion becomes ferromagnetic? Okay, here we have some experimental results, magnetic force microscopy images. We have here nice images, is beautiful patterns obtained by AFM in the magnetic force mode. So we have dark and light bands here, which are characteristic signature of the remnant magnetic domains. So these they are known as the stripe domains, which is a clear indication of the ferromagnetism in the expanded layer. This stripe domain structure, the magnet is a clear evidence for significant out-of-plane magnetization. So this is like white and dark spots here, all these stripes. Let's say the white regions are like the net magnetization out of the page. The dark regions are net magnetization into the page, okay? So also it's kind of interesting, as I said, this material is polycrystal material as a result of nitrogen ion implantation. There are many single grain effects here. For example, also magnetic behavior changes from one grain to another, okay? We have also done, some magnetic force microscopy measurements again here. We have done the vibrating sample magnetometry measurements on our nitrogen implanted sample. There's a clear indication of the loop behavior here, hysteresis behavior, which also shows that this layer, nitrogen implanted layer, force becomes has a ferromagnetic behavior. We have done MOC measurements, magneto-optic curve effect measurements on one of the samples, because the other samples, they were kind of rather rough because of nitrogen implantation. Surfaces become rougher, so it's not easy to collect signal, because in this MOC is a very surface sensitive technique. So the higher implantation times result in higher rougher surfaces. But mainly here, hysteresis loops, MOC and VSM demonstrate ferromagnetic type of behavior based on these like VSM data parameters, like the coercive field and other parameters. This implanted layer is basically soft ferromagnet, such as soft iron. Okay, so to understand the physical origins of this ferromagnetism in the implanted layer in this phase, basically the basic reason is lattice expansion. Okay, so you put nitrogen into the FCC lattice of this substrate material. Nitrogen in octahedral size expands this lattice. Remember, the original lattice, original material is paramagnetic, but as a result of this expansion, and this expansion is like as high as 10%. Why this 10%? This due to the nitrogen beam. Nitrogen contents may reach up to 30 atomic percent in the layer. So we could correlate the ferromagnetic behavior of this phase with FCC gamma iron. As you may know, iron has different lattice structure. One of them is like, for example, BCC, body centered cubic, alpha phase. Iron, pure iron also. I'm talking about the pure iron. Also, it has a FCC crystal structure, which we call gamma. Literature studies, quantum calculations show that the iron, FCC gamma iron phase has two distinct magnetic states. One is a high volume, high spin state. The other one is a low volume, low spin state. In our case, we correlate our ferromagnetic expanded phase with a high volume, high moment FCC iron state, okay? Of course, we have not done any quantum calculations on this on this phase. So these are the literature results, quantum calculations, energy, moment calculations. Here, you could see that FCC phase of like iron, FCC phase of the iron here, at a critical lattice parameter, moment is quite low, but at some critical parameter, it reaches a high moment. So as a result of nitrogen implantation, there's an expansion of the lattice. So we think that we could correlate ferromagnetism of this phase with a high volume, high moment FCC iron state, okay? Okay, how I'm doing on time? I have a few more minutes, I guess. So we could also correlate ferromagnetic behavior of this expanded phase with iron nitride phase, which is also a phase-centered cubic crystal structure known as gamma prime phase. This is like FCC lattice of iron. Iron atoms in the corners on the also phase centers, and nitrogen atom is in the octahedral site in the center of the FCC lattice. Okay, so it has an FCC structure. This phase is ferromagnetic. The difference between the expanded phase gamma sub-N and iron nitride Fe4N phase, Fe4N is ordered while gamma sub-N is disordered. So it's interesting that the onset of gamma sub-N ferromagnetism is similar to gamma prime phase, which has a 20 atomic % nitrogen in it. Remember, our phase, our implanted layer phase, becomes ferromagnetic for high nitrogen contents, and for low nitrogen contents, this phase is paramagnetic. Okay, well, so what happens? Okay, let's just summarize the physical reasons for ferromagnetism in the expanded phase. Basically, fundamentally, it has to do with the electronic structure of iron, okay, which is the main element in stainless steel, okay. Of course, it has to do with the strength of the iron-iron magnetic exchange interactions, which depends strongly on the orbital overlap. Of course, iron is like 3D material. Basically, the interatomic distance, okay? You put nitrogen into the lattice, there's an expansion, okay? So iron-iron distance changes, which changes the magnetic interactions. But what about the nitrogen? Of course, nitrogen atoms in the octahedral size modifies the electronic structure of iron. So that might maybe reduce the magnetic effect. Expanding the lattice reduce this overlap, 3D overlap, enhancing iron magnetic moment, okay? Okay, let me say a few things about the conclusions. Our implantation conditions, which we call low energy, high flux nitrogen ion beam conditions, apply to 316 stainless steel material at a substrate temperature of 400 degrees C, results in an expanded phase, gamma sub-N. on the source of this material. Stripe domains observed by MFM, magnetic force microscopy, and hysteresis loops by MOC and VSM suggest ferromagnetic type of behavior for this layer on the stainless steel substrate. Ferromagnetic state is mainly linked to large lattice expansions as high as 10%, and which is due to the high nitrogen contents, which may be in this case like as high as 30 atomic percent. Magnetism of expanded phase is very much related to ferromagnetic state of this phase, FCC gamma prime nitride, Fe4N, eventually to the magnetic properties of the FCC gamma iron phase, okay, pure iron phase. So, of course, this is like a kind of spin-off of this implantation work, because we were mainly interested in the friction, wear, corrosion properties of these surface layers. But we have a magnetic layer on a non-magnetic substrate. Perhaps this might have some, for industry, we might have hard layers, also magnetic layers for magnetic applications. I guess I'm done, but I would like to acknowledge a few people here. Our colleagues are Prof. Ahmet Öztarhan of Ege University for ion implantation, plasma nitriding, and cotton work. I worked with Ahmet Öztarhan for a number of years. Unfortunately, I think he's one of the pioneers in Turkey for like doing industrial type of ion implantation, plasma nitriding. He passed away a couple of years ago. I really appreciate his work in Turkey for industrial implantation work. And also my colleagues from Colorado, Paul Wilbur, for like providing or doing nitrogen implantation. Dr. Stefan Mendel of Leibniz Institute of Surface Modification. Also, we did some project with this person. They are quite good on implantation work. Also, Numan Aktan of Gebze Technical University for mock analysis. Again, I appreciate Turkish Physical Society's invitation, and I very much thank the organizing committee. Thank you very much.
Thank you for your presentation.
If you have any questions, let me know.
Any questions?
No questions?
No question.
No comments? Nothing?
There's no question and no comments.
No suggestions? Well, okay.
There's no suggestion. Thank you.
Right.
Thank you again for your presentation.
Okay. Okay.
Warm greetings from Bodrum.
Well, thank you very much. Have a nice day.
Have a nice day. This presentation was the last presentation. So we finish this season now. Have a nice day.
Hello, is there anyone there?
Yeah, I could hear you. I'm one of the participants, not in the organizing committee. Just to, I just sent you an email. Is that you?
Yes, Luciano, yes. Who is that? Hello.
I'm Orhan. I'm not in the organizing committee. I'm just a listener. I can hear you, so I think it will start soon.
Okay, can you see me? Because
I could see you. Yes, I could see you. I could hear you. I'm one of the participants, not in the organizing committee. Just to, yeah.
Okay.
I just sent you an email. Just fine. Is that you?
Yes, Luciano, yes. Who is that? Hello.
I'm Orhan. I'm not in the organizing committee. I'm just a listener. I can hear you, so I think it will start soon.
Okay, can you see me? Because
I could see you. Yes, I could see you. I could hear you. I'm one of the participants, not in the organizing committee. Just to, yeah.
Okay.
I just sent you an email. Just fine. Is that you?
Hi, Luciano. We can see you and hear you.
Can anyone hear me and do something about and instruct me about what I should do?
Yes, Luciano, I can hear you.
Okay, but I don't hear anything from the organizing committee.
That's a pity. Yeah.
You know, the link they had given me was wrong.
Hear me and do something about and instruct me about what I should do.
Yeah, now there is a loop.
Yes, Luciano, I can hear. There is something strange.
başlasın, sunumda yazsın.
Evet.
Teknikler, sen de moderatör.
Dear participants, welcome to this section, and we would like to have a nice conference and hope you will enjoy in this section. And our first speaker is Professor Luciano Rezzallo, and he's going to topic the first image of a black hole. Please come in.
Okay, can you hear me?
Okay, you can start now.
Yes, can you hear me?
We don't hear you. Could you open your voice?
My mic is open.
Yes, we are hearing now, and you can start.
Okay, so I will start sharing my screen. Hold on a second. I hope you can see my screen now.
Yes, we can.
Okay. Well, first of all, thank you very much for the kind invitation. I am extremely upset that I cannot be there in person. I really wished I could come. I had made long plans about coming to Bodrum and participating to this conference, but COVID has prevented me from officially taking place to this conference. But nevertheless, I would like to thank you for the kind invitation, and I'll give you this presentation on the first image of a black hole. Here is what I want to talk to you about. First of all, how you take a picture of a black hole from an observational point of view, then how you do this from a theoretical point of view, and then comparing theory and observations. And finally, I'll spend some time, if I have, telling you about alternatives to Einstein theory and to black holes even. So this is, let's start with a very basic problem. Black holes are the most compact objects in nature. You cannot confine mass or energy in a smaller volume. And this means that you need something which is big. And so the black holes you need are astrophysical black holes, but these black holes are also at astronomical distances, so very large distances. And you can imagine that if you have something which is very small and very distant, then it will appear on the sky as extremely small. So if you want to take the photo of a black hole, you need a black hole which has a size on the sky which is resolvable by your instrument, by your telescope. And this essentially restricts the problem to having a very massive black hole, the biggest you can have around, and a sufficiently close distance. And we had two perfect candidates for this, satisfying these constraints. One is M87. M87 is a supermassive galaxy, and something we know since centuries. This is an image in the optical. I hope you can see my pointer. And you can see there is a little filament over here. This is an extragalactic jet which is powered and is moving at speeds closer to the speed of light. If you look at this very same object in the radio, you see it's much larger, several 100,000 light years in size. And you can use a technique which allows you to go and zoom in into the inner part of this region. Say, you can have a look at a closer picture of the inner part of M87, and you can further close in and have a picture which is just concentrating on the launching part of the jet. And you can even just concentrate on the very close to the launching site. And the purpose of the Event Horizon Telescope was to take a picture with a resolution as the one indicated over here. So it's a teeny tiny spot as compared to what people were able to do before. How do you do this? Well, you use this technique, which is called VLBI, or very long baseline interferometry. This technique relies on a very simple expression. Given a resolution you want to reach, this is given by the ratio between the wavelength at which you make the observation and the telescope size. In the case of the wavelength, we want something that reaches us, and so it has to be not absorbed. And this essentially leaves radio waves. Radio waves are the only waves that can go through all the interstellar medium between us and the source without being absorbed. Other radiation is emitted near the black hole, but this is trapped before it reaches us. And then you need a telescope. What is the telescope you can put here? Well, you can put the size of a radio telescope, few tens or few hundreds meters, but that would not be sufficient. You need something much smaller if you want to have the something much larger if you want to have a resolution, which is the one that I was showing you in the previous slide. So how do you do this? The idea is to create a virtual radio telescope, which is as big as the Earth. So you take telescopes scattered across the world. These are, medium size, 20, 30, 50 meters in diameter. And then you put them into an interferometric connection. Essentially, you can have a telescope in Arizona, a telescope in Hawaii, and make sure that they are capturing exactly the same light or the same wavefront. And if you do this, then you have a telescope which has the virtual size of 2,000 kilometers. That is the distance between Hawaii and Arizona. Now, it's obvious that there is a little catch here. In order for this to work, you have to make sure that you are really observing exactly the same electromagnetic wave, the same wavefront. And that is why all of these telescopes have not only sufficiently sensitive receivers, but also atomic clocks, so that they record not only the electric field as it is received, but also the time of arrival of this electric field. And in this way, you can actually do interferometry. And then you can have a network of telescopes, which will allow you to have different separations, different distances, and this will give you different, it's like having different telescopes or different resolutions in this formula. So that's what we have done in 2017. And as you can see, there were people who were doing observation in Mexico, in Chile, the South Pole, at Hawaii, in Arizona, in Spain. And if you notice, all people in these photos are happy. And the reason why they are happy and smiling is because everywhere in all the different sites, the weather was good. There was sunshine, there were no clouds. And this is very important to us because water vapor is a very good absorber of these radio waves. And so it's sufficient that you have a cloud a few kilometers above your telescope, that light is trapped and you will not see the light that is coming from the source. And the source is 55 million light years away, but it's sufficient that you have an obstacle right at the end, and that's it. So as I've explained, you have different telescopes with different lengths. They provide information or tracks in this space, which is called the UV space, or the visibility space. And out of these tracks, you can build a certain picture, a certain image. And as time goes on and the tracks becomes larger and you fill this space, this is a Fourier space, essentially, you have that a sharper picture emerges. And that's exactly what we've done. As you can see in this animation, as the Earth rotates, the tracks are being filled, the UV plane is being filled, and you have different scales that are being provided and a sharper and sharper image. So at the end of the day, at the end of collecting the data, cleaning it up, calibrating, the observers have provided us with these 4 pictures, 4 images. And as you can see, they're all very similar, but they are not identical. And that's exactly what you would expect. And my role at this point was trying to make sense of these images, explain what these images are and why they look like that. And that's what I want to explain to you in the rest of my talk. So from a theoretical point of view, you need 3 steps in order for understanding what that picture means. First of all, you need a GRMHD simulation. These are simulations of general relativistic magneto-hydrodynamics, and essentially tell you and teach us what happens to plasma that is falling onto a black hole. Now, this plasma is going to emit light, and this light needs to be traced and tracked back as it moves in a complicated curved space-time so that we can make an image. And we need to calculate how much light is absorbed and is emitted as it moves through its trajectory, its geodesic trajectory. And I will explain it is far less obvious than you may think of in a curved space-time. And then we have to compare all the possible theoretical possibilities and synthetic images with the observations. In Europe, we were very lucky that we had substantial grants, ERC grant, a synergy grant, which is called Black Hole CAM, with which we have built essentially 3 computational infrastructure for doing these 3 different steps that I mentioned here. And the real heroes of this effort are the people that I list here, who really have done all the work behind what I will present here today. So these are the equations that we solve. As a theorist, this is the way I like to think of my problem. I need to solve on a curved background. That's why you have a covariant derivative over here, conservation of energy and momentum, conservation of rest mass, you need an equation of state, and you need to do this assuming not only a fluid, but also electromagnetic fields, and therefore you need also the solution of the Maxwell equations. All of this needs to be done in 3D, and in addition, you need the general relativistic radiative transfer. So you want to study again, essentially a Boltzmann equation for the intensity of the radiation as this parcel of radiation moves in the plasma towards the observer. This is an example of what happens to plasma when it is accreting onto a black hole. I hope you can see this movie. You can see that there is a red, yellow, this is density, rest mass density, and there is another quantity, which is the magnetization, this white, blue color. This is where there is a lot of magnetic field and very little matter, and here is where there is a lot of matter and very little magnetic field. And as you can see from the actual animation, the accretion process is not steady. It's very turbulent because there is an instability that drives accretion. It's the magnetorotational instability. And so matter falls onto a black hole at irregular rates, just like a waterfall. We provide a steady state, but eventually only and statistically, every now and then there is more water, less water. This is the inclination in which we think we are looking at M87. And now you have to imagine we see the actual radio emission. You see it's almost a uniform ring, but this is just because we are in this very special inclination. If we start looking at how the radiation field changes as we move our position, you see that it's a very complicated structure. And if we now imagine what a telescope would see, this is what it would see, essentially a blurred, flickering image on time scales of tens of hours. And that's pretty much what we have seen. So this is what we have seen. that is why we think we have a very good understanding of what is producing this donut-like image. Are you still following me, and are you still able to see my movies? Can someone reply?
There's no problem.
Okay, very good. Thank you. It's always, I always have the doubt I'm talking to myself and not to a group of people. So in order to understand why ray tracing is important, let's consider the following example. Suppose that you have a black hole and you have a thin disk of matter, which is emitting light, and you want to take a photo of this. Well, and you want to take a photo on this plate with a given angle, inclination. What you will see, you will see the light coming straight towards you on straight line, just like in a flat space-time. So you will see the forward part of the disk. Then you will see the backward part of the disk. This part over here, this is just image of the back of the disk that in principle you should not be able to see because this light should go up, but it's bent and can nevertheless reach you. And to make things even more interesting, you can see also the bottom sheet of the disk, because again, light can be bent and sent towards you. So if you now are a science fiction aficionado, then you remember this is an image coming from Interstellar. And this is a very good image. And now you could probably understand why it looks like that. You're seeing part of the disk which is in front of you, the part of the disk which is behind the black hole, and the part of the disk which is behind the disk itself, the sheet that is under. And you also learn one thing, that if you want to hide, don't go behind a black hole. It doesn't help. You will still be seen. This image is very accurate, but it's not right for a number of reasons, at least two reasons. The most important thing is that the disk, as I've shown you within simulations, are not thin. They're actually thick, geometrically thick. And so the light you should expect is more like so. And as you can see, the actual appearance will be different according to different inclinations. But what you will see also is that unless you are exactly face on, there's always going to be one portion of the image which is brighter. This is just a relativistic Doppler boosting effect that is such that for matter that is coming towards us, it will look brighter than the matter is moving away from us. And so now you probably understand why we see a donut shape. It's just because we're seeing it almost face on, but there is one part, which is the bottom part, which is coming towards us, and so it's brighter than the top part. What you can also see in all of these images is that there is a black region. This is what we call a shadow, and it's different from an event horizon. And people often confuse the two. You can't possibly image an event horizon because by definition, this is a null surface. It will absorb and prevent emission of light. In order for you to understand what the shadow is, suppose that you have a black hole and you put it in front of a source of light. So you can imagine this light will shoot photons in this direction, and then you are here as an observer. Well, there's going to be photons that go straight into the black hole. There are going to be photons that go near the black hole and then are captured. And there's going to be, therefore, an envelope, the outermost of which represents the shadow. So the shadow, this area here, is just an area where there is a deficit of light. Light here is captured either directly from the black hole or from photons that are within the photon unstable orbit. So to give you a size, in case of non-spinning black holes, you have 2m. In case of that, the photon circular orbit is 3m, and the actual projection at infinity, which is essentially the impact parameter as computed at a circular orbit, is square root of 27, and so of the order of 5.6. Okay, so what we see here is the indirect evidence that there is an event horizon because there is light that is missing. You also appreciate that this shadow is not necessarily black or pitch black. The reason is that if you take a photon here and you emit it toward the observer, this photon wouldn't have any problem reaching the observer. It's photons that are emitting from behind that are captured. So that is why in the image we have seen, the shadow is not perfectly black, and there is a depression in intensity, we call. Okay, so what are the space of parameters? As a theorist, I have no idea what is the object I'm looking at. And so I have to allow for all the possibility. I have to consider different black hole masses and spins. I can even consider alternative to black holes. And this can either be objects which are compact and do not have an horizon, or do not have a surface and also don't have an horizon. Then I have to worry about the plasma dynamics. I can have different type of accretion flows. In our jargon, we call them sane or mad type of accretion, depending on the strength of the magnetic field. And then I have to worry about the light. We believe, given the physical conditions around these supermassive black holes, that the light is produced by synchrotron emission. So a very basic process. But synchrotron emission, if you remember, depends on the energy distribution of the electrons. And we don't know what is the energy distribution of the electrons. Our simulation don't give us this information. So we need to have a modeling, an ad hoc modeling of the energy distribution of the electrons to produce the actual synchrotron emission. So we made a number of very high resolution in 3D. About half of them were run in Frankfurt. And for each of these simulation, we built scenarios where we just change the way light is emitted through different prescription for the synchrotron emission. And this ensemble gives you a very small portion of the space of parameters that we have observed. So you can see there are times where the shadow is very small, other which is very large. One is moving in one direction, the other one in the other direction, depending on whether we're looking at counter-rotating or co-rotating accretion flows, and whether we're looking at spinning black holes or non-spinning black holes, and so on. And out of this, we built 60,000 images. These are all physically consistent, physically correct, but of course may not be describing reality. And so what you have to do is compare these 60,000 images with the 4 images that you have observed. And here is where the third part of our theoretical work comes in. You need genetic algorithms that are, and essentially Markov chain Monte Carlo techniques that allow you to distinguish or find matches between the different images. And this is the kind of results we obtain. These are the observations, and this is the theoretical model. And as you can see, the match is extremely good. And because we know everything about the theoretical model, we can tell what is that we're seeing with the observations. This is partly right. What is not right is that this match between theory and observation happens way too often. So this is an example of 3 synthetic images that give equally good match. You can measure this through some mathematical gauge, but they are corresponding to completely different black holes. This one is corresponding to a spinning black hole, counter-rotating. This is corresponding to a spinning black hole, which is co-rotating. This is corresponding to a black hole, which is non-rotating at all. It's a Schwarzschild black hole. So this is a degeneracy. This is inevitable in astrophysics because you are observing things. You're not preparing an experiment. And this result is both good and bad. It's good because it gives you confidence that all of these images are of a black hole. You don't know what is the spin, and this is what is bad. With the present level of precision, we cannot distinguish the spin. And in fact, our papers do not distinguish the spin. So we are insensitive to the black hole spin given the actual observations made. But of course, as time goes on, we will be able to have better resolution, and we will be able to distinguish these models. We also have better other ways of doing this, but I don't have the time to discuss this here. So how much time do I have?
You have 5 minutes.
Okay, I'll try to squeeze into 5 minutes an important question. As a theorist, I want to make sure that I am interpreting things correctly. And of course, general relativity and Kerr black holes provide a perfect, elegant, elementary explanation for what we see. But you know, as a physicist, as we have to make sure that there aren't alternatives that provide equally good answers. And you know, this is particularly important for astrophysics, which is an observational science. And so you have degenerate explanations. I've shown you an example of degeneracy. And of course, you can ask, well, maybe it's a different theory of gravity. There are many theories of gravity nowadays on the market that provide black hole solutions, which are very similar but different from Einstein's. And how do you do this? Well, there are essentially two different ways. One which is agnostic, where you essentially don't make any priori assumption, and one where is agnostic one, where you say, okay, I test this possible solution and see whether it fits or not. In the case of an agnostic approach, this is something I have been working on for quite some time. Essentially, all you need is a background metric, and this is because we are the amount of matter falling onto the black hole is just a very teeny tiny perturbation onto the mass of the black hole. And so you don't need the field equations, you just need equations of a test fluid. And so what we have done is we have come up with a generic representation of the metric in terms of certain coordinates, plus a series of coefficients. And these coefficients, then if you take these coefficients to be equal to 0, then you end up with GR. And there are two important mathematical tricks that allow us to do this very efficiently. The first one is that we have a spatial compactification. So we have coordinates that go between 0 and 1 rather than 2 and infinity. And we have an expansion, a Padé expansion near the horizon that allows us to capture very faithfully and very rapidly the behavior of the metric function. So essentially, with very few coefficients, 3, 4, you can reproduce any known black hole metric solution that we know of. The other approach is, as I was saying, consider alternatives. And what we've done is we've considered two different alternatives, a dilaton black hole and a boson star. They're very different. This is a black hole that comes out of a string-inspired theory. This is a possible compact object which is thought to be possibly present at the center of a galaxy, is also very compact, but this one would have a shadow, but wouldn't have an horizon, would not have a surface, because it's a cloud of self-gravitating photons. So this is an example of an image from a Kerr black hole and a dilaton black hole. And you can see there are differences, but these differences are very small. And if you consider the extreme case where there is scattering, which is possible for images at the center of the galaxy, then you would see that these differences become even thinner. And so right now, given the present quality of the observation, we cannot distinguish between these two black holes. And that is why the title of my talk is not the first image of a Kerr black hole, but it's the first image of a black hole. We believe it is a black hole, but we cannot yet distinguish the theory of gravity. On the other hand, in the case of boson stars, this is pretty much the same as I was showing you before. You can see in the case of boson star, the shadow for the same mass is much smaller. And this is because, as you can imagine, because a boson star doesn't have a surface, matter can go in very close to the origin. It doesn't go to the R equals 0, but it can go very close to the origin. And so you can have light coming from the innermost regions of the shadow. And so the shadow size will be very small. And once you make a measurement of the mass, you can check whether or not the shadow size matches what is observed. So the lesson you learn from here is that it is possible to distinguish boson stars from black holes. And in particular, in the case of M87, it cannot be a boson star, at least the simplest model of a boson star. Okay, I want to come up with a conclusion. Our project has given very important contribution to the EHT campaign. We have studied Kerr black holes and other black holes to a very high level, building a lot of experience that was not present before. Essentially, all of the history of accretion onto black holes and compact objects has been rewritten over the last few years to understand better what we were observing. If you nail down what has been the contribution of the EHT, I would say that's provided the first evidence of the existence of supermassive black holes. And you can say this is a fundamental point in astrophysics. So far, supermassive black holes were always conjectured to be present at the center of the galaxy. Now we have shown that at least in one case, for one galaxy, there is a supermassive black hole. From my point of view, more as a relativist, I think the most important contribution is that for the first time, we have now a tool to test the idea of an event horizon. This is an idea that is controversial, has a lot of complications, but the EHT has transformed a theoretical concept, the event horizon, over to a testable concept from a physical point of view. And we are all physicists, we all understand how important it is to be able to carry out an experiment to check, validate, or refute a theory. And that's something that is now possible, and therefore the most important contribution in my view. Thank you for your time.
Thank you very much for your nice talk. And we can move on question part. If is there any question we can get? Yes, we have one. You can come here. Come here. Okay, we sort it out.
Thanks for your presentation. I'm questioning about that. Is there was help of Hubble telescope, and is there going to be help of the James Webb telescope?
No, as I've shown you at the beginning, you really need to have the resolution sufficient to see these objects. And these telescopes, they have fantastic resolution, but that would not be sufficient to image a black hole. Furthermore, the light that comes from very close to the horizon, the optical or the infrared that James Webb or the Hubble can provide, is absorbed. So you can't even see that light in practice.
Thanks.
Yep.
I think we have some more questions. Yes, please.
Thanks, Luciana, for the nice talk. I have a couple of questions. The first one is...
Could you introduce yourself first?
My name is Doğa. I'm a PhD student at Columbia University. My first question is, I would expect to have some dark matter densities around such heavy objects. Have you considered some dark matter scenarios in your simulations?
So, okay, sorry, go ahead with the second question.
The second question is, you said you have indirect evidence for event horizons, and you mentioned some gnostic tests for dilaton stars or boson stars. Have you considered gravastars as well?
Okay, so the first question is, you can think that a boson star is an example of dark matter, because in the case of dark matter, that's what you would expect, right? Something which is diffuse and appears as a compact concentration of some kind of scalar field. So you can think that boson star is an example of dark matter. And so in that case, if there is just dark matter, not dark matter plus a black hole, that's what you would see. You would see a very small shadow. So this seems to hint that dark matter doesn't play a role, at least it cannot be invoked as the only explanation for what we see. The second question is about the gravastar. Gravastar we haven't explored, and that's because gravastar in principle have a surface, and the interaction of the accreting matter on the surface is very complicated. People who are down to earth would say, if you have accretion onto a surface, then this surface is going to emit light, and this light will be seen. So the fact that we don't see light coming from the event horizon or very close to the event horizon is an evidence that there is no gravastar. Gravastar proponents, on the other hand, say, well, but the gravastar surface is very special, has a very high heat capacity. So matter falls onto the star surface and doesn't dissipate heat, because the heat is very quickly absorbed by the surface. As you can imagine, there is a controversy here, and people are really hand waving when they make these arguments. But from my point of view, I think the issue of whether this is a gravastar or not is still open and needs to be studied better.
Maybe I may have a last question. Can we use these images to test alternative theories for dark matter? For example, as far as I know, there are some expectations to have some axion clouds around black holes, and they may extract some angular momentum. And if I'm wrong, correct me, but I think there was a refined image recently which shows some stripes around the black hole. Can we use such information to constrain those theories?
Okay, so those were really two questions, but let's say, in principle, yes, you can constrain an alternative theories, in particular one that assumes that there is some axion field around a black hole. Once again, you have to make a prediction about what is the axion distribution, and then one can test whether this hypothesis is correct or not. The second image you were mentioning is actually a polarization. We were showing how light is polarized near the black hole, and that information helps us understand what type of accretion flow you have, whether you have one which is dominated by magnetic field or not, and what is the structure and topology of the magnetic field near the black hole. And that doesn't really help you a whole lot in determining what is the theory of gravity. It's more telling you about plasma dynamics.
Okay, thanks so much.
Thank you. Would you like to ask? And we have secondary school students.
I'm an undergrad student in Middle East Technical University. Given that we take Einstein's gravitation theory granted for these black hole images, do we use gravitational lenses to take these pictures?
So we don't take it for granted. We're testing it. So we take it as our reference because, as I said, it's the best theory we know, the most tested theory. But we don't take it for granted. We are really asking ourselves whether there are alternatives. Now, lensing, essentially, the image I've shown you is a lensed image. Lens is all about taking light and making follow strange trajectories, right? When light goes through a lens, it's being curved. So the image you're seeing is effectively a lensed image of the light that is emitted near a black hole.
Yes, and is it possible that we can use this black hole lens, this gravitational lens, to observe further images of black holes? And is it possible that within these images, can we possibly explain the singularity within black hole?
So, the singularity is within the event horizon. The event horizon is something we cannot access, so we can't really explore the singularity with these observations. What we can do is convince ourselves that Einstein is right. There is a black hole solution, which means that there is an event horizon. And if there is an event horizon, then there must be something which looks like a singularity. But we cannot possibly test it. Anything which is inside an event horizon is inaccessible to us. So what you can then hope for is, well, maybe this is a naked singularity. There is no event horizon, but there is a singularity. This is something that the equations allow for, but then a naked singularity would not behave as we've seen. So naked singularity are excluded, at least for M87.
Okay, thank you.
Thank you very much for your nice talk and these comments. And thank you to Professor Rezollah. Thanks a lot.
Well, thank you.
You are welcome. I would like to announce that there will be another talk will be added end of this section. And Professor Hakan Türeci, please, when the section is finished, we will add another talk. I would like to explain the title of talk, Machine Learning with Quantum Dynamical System. And now we are going to move on. Professor Bülent Akıncıoğlu and his talk, Next Generation Solar Cell. This talk will be on site. I would like to invite Professor Akıncıoğlu. Thank you very much.
Pointer hangisi? Şu mu? Şu. Slide de oraya. Tamam. Şu anda duyuluyor galiba. Dear face-to-face participants and online participants, first of all, I should thank the Turkish Physical Society for having me to give a talk. In fact, that nice talk about our huge universe, unbelievably billions of galaxies, billions of Milky Ways, unbelievable. We will now go to another tiny object, a very small mass, uncomparable, of the Earth, our living planet. Well, it's quite an abrupt jump, let's say. You cannot compare these two. But anyway, it's nice, right? Because we are on the Earth and we are dealing with our energy problem. Not only the energy problem, energy, environment, and economic problem. So there's a huge, huge problem. Not that huge of our universe, maybe. So we have the solar cells, photovoltaic solar cells, which is a simple diode. Discovered the last century, at the mid of the last century, very recent, the diode and the transistors, of course, in addition, those chips at the end. For the last 20 years, the technological achievements is going on. But for the last 5 years, the real technological achievements are going on. But for the last 3 years, something is happening. A very deep commercialization in renewable energy. And the first place is solar energy and the photovoltaic. Now we have about on the Earth 700 gigawatts of solar power plants, huge land. This may be another problem in future for the renewable energy. A very huge plants. Now we are covering. We have about 7 gigawatts of our 90 gigawatts. 7 gigawatts of our power plants is solar energy, photovoltaic, of our total, together with the fossil fuels, of 90 gigawatts. It's something about, as far as I remember, about 7% of our energy is now coming from the solar energy, coming from the photovoltaic system. So we should move to the next slide. Yes, that's it. So there are actually 3 types of solar cells. The first 2 is the first, and the second is the second generations. And the third is called as the third generation. But it's not the third, because it should be next generation, because there are too many things. Although it's a very simple physical mechanism behind, this is quite simple. And in this talk, we'll mainly talk about the physics, the simple physics, and how that next generation solar cell is coming, probably in the next 5 years, maybe 10. Those power plants of the solar energy, photovoltaics, will be changed before their life, because it was before 25% of efficiency. Now we are talking about 80% of efficiency. It's something in that next generation cells. And this is the silicon blocks produced by the Chakarovsky crystal growth systems. mainly. And now we can grow these blocks. Turkey, a very big company, doing now, too. And you can cut these blocks, crystals, these blocks into planes, into wafers, and these wafers are used for the photovoltaic cells, for the diode. It's a simple diode, that solar cell. But in these blocks, you can put many, many transistors, very small transistors, very, very small. Now it's end of the molecular structure. We can produce device within molecular structures. This is the end, Moore's law. So that those chips are from those very, very small objects. And some organizations and some companies are in Turkey are doing these chips as a test chips. And silicon monocrystal is the first generation. Single crystal, one band. The second is the thin film, the second generation. That silicon monocrystals have a little higher efficiency than the thin film. It's about 24% maximum, well, about maximum, let's say. But for the thin film, it's in between 3 to 16%, it's changing. But some of the thin films, special applications, have larger than 2024, but they are special thin films, very small amount. And mainly now on Earth, it is the silicon monocrystal structures. About 95% of the commercial photovoltaic power plants have that silicon monocrystals. Monocrystal, actually, crystal or polycrystal solar cells. The others are the thin films, and that very, very small amount are some other systems. Now, and the next generation, the third or the next. In the next generation, that 24% or that thermodynamic limit is about 30%. Every system, every structure has a thermodynamic limit. You can calculate, you can find this thermodynamic limit by using energy conservation principles, energy and momentum conservation principles. We are working with the energy and momentum conservation principle, even for the black hole. That very huge mass, unbelievably huge mass. It's not quite understandable. Also, simple facts, even to the quantum mechanics. So this is an example. It's an example of the new generation. We say it's the down converter. So we have different structure here. I will be talking about this. So, and what about the generations, those generations? This is a diagram produced by a very famous photovoltaic pioneer, Martin Green. Those, not the dashed curves. Here you can see the dashed curve, always. O'yu görüyor musunuz? Böyle, okay. So, the darker ones are by Martin Green, and we just work on it. And we produce those new generation for the first generation, for the second generation, and for the new generation itself. So the efficiency is going up. You know, on the left side, we have the efficiency. And on the horizontal side, module cost. It's kind of a relative diagram. So you see how module cost is increasing with the efficiency of increase, unbelievably increasing, exponentially increasing. That's why it's only 24% now we are working. And in the field, in fact, it's less than 24%. It's in the laboratory 24% or 20 to 23%. But in the field, it goes to the 16%. In our works, now recent studies, it's less than 16% on the Earth, on the you know, those power plants, very huge power plants. For example, for 1 megawatt, we need about 10,000 meters square area. So more than that. So those dashed curves, for example, the leftist one, the dashed curve, is for the next generation cells. So it can go up to 70%. Even some in some theoretical calculations, it goes up to the 80%. So it's 80% is unbelievable because we are now using 20% efficiency solar cells. If it is 80% for the next generation, is about 1/4 of the Earth's surface that we will be using to produce electricity by using these power plants. So it's something, because you are just covering very huge lands, and we have another problem. One of our students is working on this. Heat island effect. Heat island effect will be another problem. But let me continue, because we have to talk about the next generation, only the physical mechanisms, the basic physical mechanisms. So this is the solar spectrum, maybe some of you know. And here you can see this part. This part is the UV, this part is the visible, and this part is the near infrared. A little part we have in the UV from 0.25 micrometer wavelength to the 0.40 micrometer, from 0.40 to 0.7 micrometer in terms of wavelength. We have the visible and we have the near infrared part. We are only using this part, a very small spectrum of the electromagnetic wave. So I will come to this point. You see, this is rough crystalline on the left, and these are the wafers. It's a semiconductor, as you may know. It's not a conductor or it's not an insulator, because it's a band gap, conduction band and the valence band, and because it's diode. And from the valence band to the conduction band, electron can be excited to produce electricity. Very simple. So this is the simple physics. You know this expression, a very important, simple but very important expression of Planck, that photon energy is h nu. Planck, was not forcing his Planck constant, h. Later, Einstein said that this is an important constant. So it's that value. And by using, of course, that h nu can be written as hc over lambda. That hc is 1,240 electron volt nanometer. You can simply do these calculations now with your calculator, with your phone, cellular phone. And for the lambda wavelength of the electromagnetic wave of sound, 0.550 micrometer. This is the center of the solar spectrum. We have about that amount of frequency corresponding to that wavelength. You can either describe the electromagnetic spectrum by using the wavelength, or by using the frequency, or by using the energy. So on the left we have the energy. On the second expression is the frequency, and the third expression is the lambda. Some people just go with the wavelength, some people go with the energy. They are all the same. They just explain all the same similar physical properties, physical mechanisms. And there's a simple calculation here. This is a simple equation. But of course, next generation has some different structures, producing from this simple physics some new generations, new structures of 80% efficiency. And it's the same spectrum. So you see those cells. This is cadmium telluride. This is gallium arsenide. This is cadmium sulfide. This is silicon. These are the energy band of these crystals, these semiconductors. This is 1.1 micrometer. It just corresponds to 1.1 electrovolt in the energy side, or electrovolt of the photon, of course. Of course, it's a quantum mechanical aspect that we are talking about. So this is şöyle yapıyoruz, değil mi? Okay, so this is again an example of the cells. The first one is the thin film, the second is the monocrystalline, and the third one is the polycrystalline. You can see the shapes and the geometries, etc. And on the first down is the solar cell produced in Yunnan, in Matthew, and on the right, those are mini cells. Now we are producing for a project, European Union project, small cells, mini cells.
Is there a problem? I cannot hear. Can you hear the speaker?
I cannot.
No, we cannot.
There's a problem, I think.
Yeah.
Extra energy, because when you have photon coming from the sun, which has the energy at the band gap, then you can produce an electron hole pair. But if the photon energy is less than the band gap, you cannot produce electron hole pair. It is larger than the band gap, okay, you can produce electron hole pair, but the amount of that energy, larger than the band gap, you know, it's just converted into thermal energy. It cannot produce electron hole pair. So with the thermal energy, the photovoltaic cell is heated. That thermalization, the temperature increase, decrease the efficiency. It's the inverse effect. If you can also collect that part, the lower energy and the higher energy, then you can do it. That intermediate band structure can do this. Lower energy photons can be used, absorbed, and produce an electron hole pair. Extra. So your system goes to the more than 50% efficiency. If you can manage to construct, in the laboratory, they can construct. But commercial, if you want to do it commercially, if it's highly costed systems, they will become cheaper and cheaper, for sure, it seems for sure. So, but in the next 5 years or 10 years, as I said, they will all be commercial. Some of them are commercially available, and a company now in Turkey producing one of these next generation cells, and this is also it's already started to be commercialized. We are working on this cells for about the last 1 year or 1.5 years, and what we obtain is about it's 7% higher than the usual cells. 7% higher means not the efficiency, the total energy production. It's about 1.5% higher efficiency, those bifacial, we call it bifacial next generation cell. I will talk on this also. So this is multiple carrier excitation. So you see here, by one photon, the photon energy is higher than the band gap. So you see, this electron is now there and the hole is now there. So the energy, extra energy, can be converted into another photon or another 2 photons. So that extra energy is not becoming a thermal energy. You just use it to produce another photon. So it's a kind of a win-win. This is called multiple carrier. So you can produce multiple carrier electrons. So you can produce more than one electron hole pair by using that band or that energy of a photon coming from the sun. And this is the last mechanism that I want to discuss. This is hot carrier extraction. And also this diagram is a kind of a connected, interrelated structure. We have 3 different physical mechanisms involved. Maybe it will be better to just study this in detail. but it also explains what these next generations are. So some of them, for example, the intermediate band, very challenging structures to produce that intermediate band, because you can just, you have different physical interruptions to the structure. For example, you can put some extra molecules, small amount of extra molecules to produce intermediate levels, or you can just change the atomic structure of the system, crystal system or polycrystal system, just by working with the atomic structure. So you have various ways to produce that intermediate band. If you can do this, then you will have extra electron hole pairs by using higher energy photons or by using lower energy photons to produce electricity at the end, of course. So these are the novel designs. Here we have a review article, which is a recent article, May 2021. So this is a review, it's published. This is a review article on the next generation. We just made the classification, the classification of physical mechanisms, and also classification of these new novel designs, laboratory designs. Only one of them, this one, bifacial, is commercialized now, started to be commercialized. That's what we are working on still with that company, producing the company, directly producing these cells. In Turkey now we can produce cells, solar cells. The company isn't also in the laboratories we can produce, of course. So the first one is heterojunction with intrinsic solar cells. This heterojunction we are using. Bifacial, dye-synthesized are the new generations again. They are for some special purposes. And quantum dot solar cells, so quantum dot also acts in a structure. If you put that quantum dots, small dots, in micro level, less than micro level dots, nanometer levels. And we have organic solar cells. This is also for some special purposes. And we have multi-junction solar cells, more than one junction. For example, perovskite we have now. Perovskite is now started to be commercialized. Perovskite together with the silicon produce two junctions. Two junctions produce more than one electron hole pair, of course. In one of the junction, some of the photons are used. In the other junction, the other photons are used to produce but the problem is, of course, to produce electron hole pairs, okay. But the time they recombine, they easily recombine. But the time before they are relaxed, before they are recombined, it's just about 10 to minus 8 seconds in a very short time. If you increase this time, 10 to minus 6 seconds, then you will have more electricity. This is another problem that they are trying to solve. And they are solving, in some of the laboratories, this problem also in the laboratory. And the luminescent solar concentrator we already discussed. And if you read this article, because all these new novel designs are also explained in details in this article, because it's not time to discuss all of these cells. Now, concluding remarks is the conclusion of that article. The photovoltaic cells have been intensively studied during the last decades. These devices provide the most elegant form of obtaining renewable energy, since on one hand, they are using an inexhaustible source of energy. We say inexhaustible source of energy. Solar energy, renewable energy is inexhaustible source. It's not like the wind energy. For the wind energy, for example, for Turkey, total potential is about 40 gigawatt. But for the sun, for the solar energy, it's about more than 300 gigawatt for Turkey. You think about that. We are now using about 90 gigawatt of energy from all our plants. We have about 300 gigawatts, more than 300 gigawatts of solar photovoltaic energy, solar energy. Of course, we cannot use all the lands of the country. So this 300 gigawatt is the lands which we can use to install photovoltaic systems, photovoltaic structures. And they do not have moving parts. They do not have moving parts. In systems, when you have a moving part, it's a It's a double problem, or more than a double problem. There is no moving parts. This is another, of course, important issue. Making their operation and maintenance easier as compared with other renewable energy devices, compared to the wind or the other renewables, is better. And that paper focuses on the recent advances in the field of solar cells, as I already discussed. And a few comments is given also about somehow confusing existing it is still confusing existing terminology we have international level. We already discussed this in the international conferences. So the basic physics which should be known in order to understand the present research direction are presented in this article, where the main mechanism envisaged for improving the PV cells performance are also discussed. So what should do this performance? Durability, stability, and also efficiency. So these three things together should be improved, of course. And it will be improved. And I think this is all. Thanks for listening. If you have any questions on these issues, I'm ready to answer. Thank you for listening.
Much for your talk. And if you have any question, we can have it.
Thanks a lot. I have two questions. First of them, how next generation cells can produce more efficiency, because which technique can help in that way?
Yeah. Now we have the thermodynamical limit. This thermodynamical limit can be done easily by using energy conservation principles, energy and momentum conservation principles. But just by using, in a broad sense, to find the maximum value that we can reach. You can never reach that maximum value because you are using the properties of the materials. With for example, the properties of the silicon cells together with the module technologies, etc. There are many properties. So using these properties and the energy conservation principles, mainly heat transfer and radiative heat transfer, convective heat transfer, we have conduction heat transfer and radiative heat transfer. We use all these heat transfer mechanisms to produce. It's not that hard to produce that thermodynamical limit. For the monosilicon cells, it is 30%. We cannot go more than 30%. But for these next generations, together with using with the fluorescence concentrator, together with using the intermediate band, you can increase the number of electron hole pairs from each photon. This is called quantum efficiency. There's a number of electrons that you can produce by using a number of photons. If you divide the number of electrons you produce to the photons which is coming from the sun, then it's quantum efficient. Then that quantum efficiency is increasing in the laboratory, those next generation, just by putting some extra layers, semiconducting materials, or even very thin conducting structures between the junctions. We have positive semiconductor and negative semiconductor come together. It's PN junction, it's diode. So if you just put some thin layers, some extra things in the structure, then you can produce more than 30% efficiency, up to the 80%. In the laboratory, they are doing it, some of these structures. But the future will be 80%. Will go up to the 80%, maybe, probably. I should think. But that's the answer to your question, I think, right?
Yes, actually, is it like atomic electronic layers, right? That you said in solar panels.
Now we have conductors, we have insulators, and we have semiconductors. Conductors are conducting materials. That energy band diagram, the conductor does not have such a diagram. The energy levels of the electrons that are located, right? And in the insulators, that band, that difference between the energy bands is very, very large. That is why insulator. But if it is a very proper value, then it's semiconductor. It's the silicon crystal. So it's a semiconductor, and that value is 1.1 electron volts for the silicon. So that's why we can take this electron at the level of valence band to the conduction band. Conduction band, it means that you can use it to produce electricity. Not only the electrons, and also the holes behind, both just gives electricity together with whole end, because whole means, you know, when you take the electron up, then there is an atom behind. That atom has one electron missing. When there is one electron missing, it is also a charge. With a positive charge. You have the positive charge and you have the electron negative charge. You can use both of these two elements to produce electricity. Is it clear?
Yes, yes.
Okay.
So another question is how we can take that we can use solar energy while that cloud.
While what?
While cloudy day.
Yeah, this is also a very good question. Even in some of the social science people, well, is there any social science people? Hope no. So they ask this question: what will you do when there is a cloud? When there is a cloud, about 30% of the energy coming from the sun is reaching us. But the remaining 70% of the sun coming from the sun after the atmosphere, because it's cloud, is not reaching. But 30% of the sun, which is coming through the atmosphere, we are using in the photovoltaic system. It also uses. But of course, for example, when it is a clear day, the energy that you can extract is A from a system. But if there is a cloud, the energy that you can extract is A over 3. You're still pumping energy to the grid, electricity. And you can do it directly, and you can do it by using accumulators or by using the lithium-ion batteries. So now it's on the way. Now, Israel, like in some other Scandinavian countries, they are producing a better lithium-ion battery. Also, some of the people in Turkey are working on the lithium-ion batteries. And lithium-ion batteries now it's coming, then you can also store the solar energy. Not only you can directly use to the grid, you can also store it and use it during the night. This is the new information that I'm trying to give. And also rooftop system rooftop system. In almost all the roofs, well, almost all, roofs will be covered by the solar energy system now. In Germany now, one of the city, the roof of the buildings, residential buildings, covered with the solar cells, all of them. Maybe some of you have heard it, Freiburg. So now Turkey is also started. In this respect, Turkey is in a good position compared to maybe many European countries. So that's why the rooftop systems are coming. But of course, we just keep in mind that increasing the number of solar cells, increasing the number in the field, produce another problem. This is heat island effect. Heat island effect is an important problem because now in Bodrum we have a heat island. This is called thermal pollution. Around Bodrum, the temperature on the average of the temperature around the Bodrum on Bodrum is about 10 degrees difference. So this is a pollution, you know, human-induced pollution. We are also polluting by just producing cities, towns, etc. This thermal pollution is another problem. For the thermal pollution, we should also spend money to produce energy. So and that's why this is another view. We should think about renewable energy, but we should also think about how it will be in the future for the heat island effect or for some other things. So another problem is the waste, because 20 years from now on, some of the power plants will be as waste products. What will you do with the waste products? There is only one institute now working on this, waste. And we have a master student, now she's with us. So she's also working on this waste issue.
I think we are over time.
Okay.
That's why okay. you can also discuss after this. Professor Akınoğlu, and we are going to move on our next speaker, Professor Pierre Scivi. The title of his work, Action Dark Matter. Can start.
Okay, I have to share screen, right? Okay.
Yes, you can start if you like.
Okay, very good. Can you see this? Can you hear me? Okay, well, thank you very much for having me at your
Could you
meeting.
please
in
open
Bodrum.
your voice, please?
Oh, okay. Can you hear me now? So can you hear me?
I can hear. There is no problem as far as I know.
We don't still hear.
Okay, they can hear me online. Can you hear me in the auditorium?
Okay, we can hear you. You could start, please.
Okay, thank you.
Thank you. Thank you very much.
So I'm sorry I could not come to your beautiful site, Bodrum. It looks very, very beautiful. I'm going to talk about axion dark matter. Specifically, I would like to compare axion dark matter with other forms of dark matter and point out differences which may be observable. Before I start, oops. Oh no. Okay, before I start, I would like to share this picture of Feza Gürsey, who is a beloved physicist in Turkey, I believe, and in the US, and he was my advisor at Yale University in the early 1970s. So also I like to acknowledge my collaborators, Charlie Yang and Özgür Erken, Haywood Tam, Nilanjan Banik, and Elisa Todorello. So today we ask, what is the dark matter? And I thought it might be useful to take a historical look. If you go back, I guess 4 centuries, after much had been achieved in classical mechanics, people then asked, what is the nature of light? Light seems to be a very strange thing. It comes and goes, and it goes through windows, and it goes extremely fast. And it took a while to figure this out. Now, as you know, originally Newton thought light is a stream of particles, with Huygens thought it was a wave propagating. And then Young did experiments and showed the interference pattern, and that seemed to definitely show that light is a wave. But there's more to the story. Oops. Somehow, because Planck then pointed out, by discussing the blackbody radiation, that light is in fact a stream of photons. So we have at a fundamental level a duality between particles and waves. And quantum field theory gives actually a description of this, which is satisfactory. Quantum field theory says that if you consider a field like the electromagnetic field, you should consider it to be a sum of oscillators, and each oscillator is quantized. So there is a Hamiltonian for each oscillator, which is like that of the harmonic oscillator. So we construct quantum fields out of these waves, multiplying them by annihilation and creation operators, and that makes a quantum field. Now, I've listed here all the quantum fields that we know of, except I did not show the graviton, but the graviton is presumably also a quantum field. So these are the particles, so-called, of the standard model: the leptons, the electron, the electron neutrino and so forth, the quarks, the photon, the W, the Z, the gluons, and then the Higgs particle. And we are interested in what is the dark matter. Well, most of these particles don't actually are not adequate because they're unstable. Of course, the dark matter should be a stable particle, so that eliminates most. Actually, the most obvious candidates are the neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino. But these particles move too fast to easily gather in galactic halos. And so they're called hot dark matter. They're not really acceptable candidates. We need cold dark matter. Another candidate is made out of baryons. That is to say, you make quarks, combine them into nuclei, and that's called baryonic dark matter. But that's also inadequate because the fraction of the contribution of baryons to the energy density is too small. We know this from primordial nucleosynthesis and from the cosmic microwave background. And so that's also not working. So there must be an addition to this collection of fields that is a field describing dark matter, and we're wondering what it is. Now, in asking what it is, I think people are heavily prejudiced towards a particle because most of the time when we see things around us, we see particles. The wave nature is much less evident most of the time. Of course, the photon is the exception. So I was very much excited, I think, to see this picture of atoms interfering with one another. So this is from Cataly's lab, and it shows a Bose-Einstein condensate of atoms, and then another one, and then when they overlap, the two condensates interfere with one another, and you see this pattern. So in fact, everything, as we know, has this possibility to be appearing as a wave. So the dark matter could be a wave, it could be a particle. So I want to discuss how you go from quantum field theory to these different limits, particles and waves. So, you know, the quantum field theory Hilbert space is a so-called Fock space. You consider all the possible waves in the field, and then you say each wave, say number 2, can be occupied by n2 quanta, and same for all the others. The limit of single particle quantum mechanics is when you put all the quanta into a single wave and no quanta in the other waves. And then if you work it through, you'll have for this one quantum, if it's a non-relativistic particle, you'll have the Schrödinger equation. And as you know, it has a probabilistic interpretation. Now, if you do it for one photon, you'll get a wave equation that you normally think of as a consequence of Maxwell's equations. But I want to emphasize that these two equations are really on the same footing. If you have a single photon, then this is a wave equation with a probabilistic interpretation where you will find the photon. Okay, so that's quantum mechanics. How about classical mechanics? So there's two different limits of two different ways you can obtain classical behavior from quantum field theory. First, you go, one way is the so-called classical particle limit. You go from quantum field theory to quantum mechanics, and then in the spirit of Ehrenfest's theorem, you go to classical mechanics. So formally, you take the limit h bar goes to 0, keeping the energy and the momentum of a particle fixed. In that limit, the frequency has to go to infinity and the wavelength has to go to 0, so that you stop being able to resolve the wave nature of the particle because omega is too large or lambda is too small. But there's a different limit, the classical field limit, which is how you obtain electrodynamics, for example, from quantum electrodynamics. Here you take h bar formally equal to 0. You keep the energy and the momentum fixed. Omega and k are also kept fixed, but then you have to put a very large number of quanta in any particular mode. So when you have a radio wave or you have an electromagnetic wave driving your cell phone, that is in the classical field limit. You have a wave which is many quanta in the same mode. Now, the previous description took h bar equal going to 0. That is actually sort of a formal mathematical treatment. In reality, of course, what people mean is h bar has a definite value, and the action of the processes that they're considering goes to infinity. So let's try to do this in a more physical way and keep h bar fixed. So then the relevant notion is actually Heisenberg uncertainty principle, which says that the dispersion in position and in momentum, the product cannot be smaller than h bar over 2. So the particle description is valid when the dispersion in position is much less than the interparticle distance. And then if you take Heisenberg uncertainty principle into account, that means that the phase space density must be much less than 1. So I just walked this through. The phase space density is the number of particles per unit volume and per unit volume in momentum space. And it has natural units of h to the minus 3. So phase space is actually, a very relevant notion to discussion of dark matter because it is collisionless, and collisionless particles are most well understood in phase space. So let's go to phase space. You have physical position and associated momentum or velocity, and you have particles when the uncertainties are sufficiently small that the little blobs in phase space are separated. So I can only draw a one-dimensional, well, two-dimensional phase space corresponding to one-dimensional physical, but of course the actual phase space is six-dimensional. It's often difficult to visualize. So if d is the interparticle distance, then the density in physical space is 1 upon d cubed. And then similarly, delta p is the spread in momentum. This is the phase space density, and you have a particle interpretation if these little blobs are well separated. That actually means n is much less than 1, curly n. Now, the wave description is valid in the opposite limit, where n, curly n, is much bigger than 1. And so now all the little globs overlap, and you have some region of phase space that's occupied by the wave. So this particular wave is a wave that, if you go to the right, the momentum increases. So to the right, the particles are moving faster, and to the left, they're moving more slowly. But all the particles overlap, and so they have quantum degeneracy. This curly n is actually the number of particles per unit of phase space. It's a number of particles in any given state. And then delta p is the momentum dispersion. Okay, that will play a role in what I'm going to say next. So just equipped with this discussion, let us look at the main candidates for the dark matter. Usually the most discussed candidate is called the WIMP, weakly interacting massive particles. So typically their mass is 10 GeV. I'm sorry, I've put units which h bar and c are equal to 1, 10 GeV. The electron is 1/2 MeV, the proton is 1 GeV, and so forth. They are produced in the early universe by freeze-out. They can annihilate, but when the universe expands, they become more and more dilute and they stop annihilating with one another. And so there's some population left over, and it is the dark matter today. This freeze-out happens at a temperature that's typically 1/20th the mass. At the time, they are still in kinetic equilibrium because they can interact with neutrinos, but then the neutrinos also become dilute and they become kinetically decoupled at the temperature in the early universe of order 1 MeV, after which they just move freely, only under the influence of gravity. Okay, if you look at them today, we know the density of dark matter, and I'm talking about the average density in the universe by multiplying omega dark matter times the critical density. And if you then take the mass of the WIMP, there's roughly 1 WIMP per meter cube, actually 0.13 per meter cubed. And from what I said before, you can calculate the momentum dispersion. Okay, because we know when the WIMPs kinetically decouple and then they get cooled by the expansion of the universe. That corresponds to a velocity dispersion. If you go in some region of the universe where there are no galaxies, say in a void, the velocity dispersion is of order 10 to the minus 12 times the speed of light. And that corresponds to with this mass, to uncertainty in position, the inverse of uncertainty in momentum of order 15 micrometers. So in fact, the WIMPs are very deeply in the regime of particles. Their quantum degeneracy is of order 10 to the minus 13. So axions are the other leading candidate. Their masses are much less, of order 10 to the minus 5 eV. They are produced by a different mechanism in the early universe called vacuum realignment, and maybe also by string radiation. Their typical momentum is the horizon at the QCD phase transition. The horizon is the age of the universe at that time, and the age of the universe is of order 10 to the minus 7 seconds when the temperature is of order 1 GeV. So take that number, take the inverse of it, that's 60 meters, and then you have to stretch that by the expansion to the universe of the universe till today, and then you get how many, well, now we obtain the density of axions by taking the density of dark matter dividing by the mass, and we find there's roughly 10 to the 8 per centimeter cube. But you have to realize that they're extremely dispersed. Their momentum so is the inverse of the 60 meters stretched to today. It corresponds to a velocity of order 10 to the minus 17 times the speed of light. That is 10 to the minus 6 centimeters per second, or 30 centimeters per year, which telling us they move extremely slowly outside of galaxies, you know. So that means their wavelength is very large. Their wavelength is of order almost as long as a light year, some fraction of a light year. And their quantum degeneracy is extremely high. It's of order 10 to the 61. So they're extremely degenerate. So thus equipped, let's ask how do WIMPs and axions differ from one another? I think it's useful to think of this blob here, which I drew arbitrarily. It could be whatever, the castle at Bodrum, or I took a blob, say an oval like this, of size a light year, okay, about 10 to the 18 centimeters. And I'm imagining that it might be made out of WIMPs or axions. And I'm sitting over here, and I only see the gravitational field because these particles interact mainly by gravity.
You have 5 minutes.
I have 5 minutes, okay. So if there are WIMPs, well, there's many WIMPs, and their position is extremely precisely determined. So there's, and I didn't draw all the WIMPs, there's 10 to the 47 of them. And you can constitute this glob very precisely in the case of WIMPs, because there's 10 to the 47 WIMPs, and there's 10 to the minus 13 WIMPs per state. So there's 10 to the 13 states per WIMPs. So in other words, the WIMPs can reproduce this glob perfectly. But in the case of axions, and I took this light here to be more or less the wavelengths of axions, then I'm much more restricted. The basic reason is that if I compute the number of axions in this globe, it's 10 to the 62, but there are, as I mentioned, 10 to the 61 axions per state. So you're very limited in how precisely you can reconstitute this globe with axions. So the basic reason for this is the low momentum dispersion, meaning a very long correlation length. If you have some wave with this Fourier transform and all the momentum in a very small region, then the density can only vary over distances equal to the inverse of this momentum dispersion, which I call the correlation length. Because if P and P prime have to be within delta P, then rho can only change when you change x by a distance of order L, called the correlation length. So since gravity is long range, the axions have necessarily large gravitational fields. Isn't that right? Because G is the gravitational field, the divergence of G is 4 pi G rho. So if the density is constant, the gravitational field must grow or go down by this order of magnitude before it can change. So regardless of the average value of the gravitational field in the axion case, this must be the typical gravitational field. So if you consider, for example, a homogeneous universe, in the WIMP case, the gravitational field is 0. And in the axion case, it is 0 too, but it fluctuates by this amount. What does that mean? If I take the momentum distribution of axions today here in blue, then it thermalizes because of these gravitational fields that itself produces. Because if you have a gravitational field delta G, you have a force m delta G. And if the momentum dispersion is delta P, it takes of order delta P over m delta G to change the moment of all the particles, that is to thermalize. If you take the distribution that I mentioned before and consider thermalization time today, it's 24 seconds. So this happened a long time ago already, because if the state of the universe had not changed, it would thermalize immediately. So when it thermalizes, all the conditions for Bose-Einstein condensation are satisfied, and we should therefore think that that is what happens. So with Charlie Yang, we found the time in the early universe when this first happens by comparing the thermalization rate here, 4 pi g rho L is the gravitational field times m divided by delta p. So this is the thermalization rate and compared with the Hubble rate. And we find that at the QCD phase transition, the thermalization rate is small compared to the Hubble rate, but the thermalization rate and the Hubble rate have different dependence upon the scale factor. And later on, because the Hubble rate goes down faster than the thermalization rate, at a temperature of order 400 eV, 400 eV photon temperature, you have this phenomenon of Bose-Einstein condensation. So I hope I have maybe a few more minutes to say quickly how axions and WIMPs differ from one another. In the case of axion dark matter, if you consider it as a fluid, it has the continuity equation and it has Euler equation where the force is given by the Newtonian gravitational potential. So this is the Euler equation, and you have the gradient of the Newtonian gravitational potential. If you put all the axions in the same state, then you also have the continuity equation. This is the wave function. This is the density, and this is the velocity field. Then the Euler equation is the same as for WIMPs, but you have an extra term, which is often referred to as, Q is often called quantum pressure. And this term is there because the axions do not want to, they tend to disperse. So if you turn off gravity and make a heap, a pile of WIMPs, well, the WIMPs will just sit there because there's no force acting upon them. But if you do the same with axions, they will tend to disperse because of the Heisenberg uncertainty principle. And this is really implemented, if you like, by this quantum pressure.
I think we have 1 minute. Is that all right?
Yes, 1 minute.
Okay.
The axion dark matter fluid therefore has a Jeans length. And this Jeans length for the numbers that I gave earlier, so for the 10 to the 14 centimeter, which is rather short compared to cosmologically observed length scales. So some people want to make the axion mass very small to make this Jeans length bigger, and this makes less observable consequences. And I wanted to point out today that if you look at on time scales larger than this thermalization time, then the axions thermalize and they do not stay in the same state. This behavior here is when all the axions stay in the same state because they move from one state to another. And this has a whole new set of observable consequences in principle, because when you move between states, you can change the vorticity of the state. And you cannot change the vorticity of the state either with WIMPs, because this is a gradient and you can show that the vorticity will not change. So the WIMP fluid will remain vorticity free. Or in the case we're putting all the axions in the same state, because again, you have two gradients. But in the actual case of the quantum axion field, it thermalizes on this scale and then can move between states. For example, here's a transition that conserves angular momentum, but the vorticity in each of the states is different. And because galaxies have angular momentum and the lowest energy state for given angular momentum is a state of rigid rotation with vorticity, you should expect that the quantum axion fluid has this ability to produce vorticity that WIMPs or classical fields do not. So that's my main conclusion. And so thank you.
Thank you very much for your talk. Thank you very much, Professor Pierre. And I think our program is over time, and if you have any question, we can have only one question. Do you have any question? All right. Thank to you, Professor Pierre Skiw again. Thanks a lot. And our next speaker is Professor Mehmet Şahin. The title of his talk, Development of Modified Detail Balance Model from Quantum Dot Nanocrystal Solar Cells. Professor Şahin.
Yes, I am here and I want to talk, I want to make this talk with online.
Okay. You can start. Thank you very much.
Okay, please let me share my screen. The host. Okay, thank you. I think everything is okay. You can see my screen.
Yes, we are seeing your screen and we are looking forward to your slides.
Okay. My presentation title is Development of a Modified Detailed Balance Model for Quantum Dot Nanocrystal Solar Cell. Here, I will talk about the detailed balance model. And first, I will talk about the model, Shockley quasar limit, and then I will mention something about the Koshal quantum dot and quantum dot nanocrystal and solar cell applications, and then we will discuss the exciton formation and recombination mechanism, and then I will talk about my modifications in detailed balance model, and I will present the results and discussion. First, the detailed balance model, as you know, is important model in the solar cell application, because this model makes strong motivation for the scientists working on the development of solar cells, and so this model is very important in the history of solar-based energy studies. And this model is developed for, by the way, I will, okay, this model developed for the PN junction solar cell. And according to this model, as you see, the efficiency, photovoltaic efficiency is 30%, is found as 30%. And what was my motivation for modification of this model? Actually, the my motivation is this paper published in IEEE Journal of Photovoltaics by Binks group from Manchester University from United Kingdom. And this group used this original detailed balance model suggested by Shockley and Quasar. But this conventional method is not appropriate for the calculation of new generation or quantum dot-based solar cells. So, because the current model does not include any parameter related to materials except band gap. This original model is based on just band gap of the solar cell. So this one, this model needs to be some modification for application to new generation or material dependent calculation of the photovoltaic conversion efficiency. Okay, the assumption of detailed balance model, as you see, in this model, there are some assumptions. These assumptions are sun and cell are assumed to be an ideal black bodies with temperatures 6,000 Kelvin and 300 Kelvin, respectively. All photons with energies equal to or greater than the band gap energy are absorbed and form electron hole pairs. This means the absorption function is like a step function. If the photon energy is smaller than the band gap energy, this photon cannot be absorbed. If photon energy is equal to band gap or greater than band gap, this means all photons can be absorbed. And again, in this model, the sole loss mechanism is the radiative recombination of the excitons. There are no other loss mechanisms. And actually, my modification is related to this loss mechanism. Okay, in this case, we can mention, at this stage, we can mention some deficiency of this model is, this model is based on gap energy only. The efficiency of any photovoltaic device is equal to that of another one with the same EG. For example, the silicon crystalline silicon band gap is 1.1 eV, and if you synthesize a quantum dot, for example, and again the effective band gap is 1.1 eV, equal to silicon. According to this model, these two materials have the same photoconversion efficiency. This is actually a lack of this model. Okay, when we look at detailed balance model, actually, in this model, everything is idealized condition, and as again the slab photovoltaic devices assumed as a black body at 300 Kelvin, and sun assumed that again a black body at 6,000 Kelvin. This is incoming incident photons, and this is emitted photons due to recombination, due to loss mechanism of the solar cell. And the current generated by an absorbed photon for one photon is given this expression. In this expression, Q is charge of the electron. The reflectivity density of the structure solar cell R is, A is absorptivity of this solar cell, and phi A is photon flux. This is current density for one absorbed photon, because again all photons absorbed if photon energy is equal or greater than the gap energy. So the total photo-generated energy, photocurrent, total photocurrent produced by absorbed photon is calculated, the integral of this one photon current. So in this case, this expression gives us this one, Here, this first prefactor called as at the same time external quantum efficiency. Here, another parameter C you can see. This C is collecting probability of the formed carriers by these photons, and phi S is photon flux density coming from the sun. And when you take this integral, you can calculate the total photogenerated current. So we can write this expression in terms of external quantum efficiency. Now we can apply the Shockley-Queisser assumptions. Again, as we said, the external quantum efficiency is equal. This expression here, CH nu collecting probability is 1. Reflectivity is 0. There is no reflection. Again, this is assumption of the Shockley-Queisser. And absorptivity is 1. Again, all photons is absorbed. So final photogenerated current can be given as this expression. As you see, this expression, this prefactor is 0 when photon energy is smaller than the gap energy of the material, and 1 when the photon energy equal or greater than gap energy. So the integral limitations boundaries actually the smaller boundary is changed with the gap energy of the materials. This is at the same time known as the short circuit current. Okay, and this is dependent only on the band gap of the material. Now, there is no problem. It's okay in these summations, assumptions. When we look at the recombination current density, we said the solar cell is assumed as the black body. So due to recombination, there will be some emitted photons, and because of this black body model, this distribution will obey the Planck distribution function. So for one recombination of one exciton, the emitted current density or recombination current density is this expression here. Epsilon H nu is the emissivity of the structure. Phi I is the again emitted photons distribution, and again this obeys the Planck distribution function. So the total recombination current is given as this expression. Here again, for quantum efficiency for the recombination is can be given this expression again for photon energy. If the photon energy is smaller than the gap energy, this is equal 0. If photon energy is greater than or equal to gap energy, this expression is 1. So finally, the recombination current density for, in original detailed balance model is given as this expression. Finally, the Shockley-Queisser equations can be summarized for photogenerated current density is this one. For recombination current density is this one. So the conversion efficiency calculation using J net current density times voltage divided by input power. The net current density is equal to difference of these two current density values, photogenerated current minus recombination current. And input power is, as you see, 100 milliwatt per centimeter square at AM 1.5. So the spectrum of this one is this terrestrial graph. Okay. And when you calculate the efficiencies using these equations, we will find this graph. As you see, this is reported in Journal of Applied Physics in 2013. And as you see, depending on the band gap, because there is just one parameter, and this parameter is just a band gap of the material. And according to this band gap material, we see that the upper limit for the solar cell, efficiency of the solar cell for different materials. But again, as I said before, for example, crystalline silicium maximum efficiency value is about 33. GIGS is again approximately the same. Or gallium arsenide, again the same. This means actually, in practically, this is not so important because there are a lot of different parameters related to materials. Okay, when we look at the literature, we can see a lot of different studies related to modification of detailed balance model, and some of the modification is related to new generation quantum dot nanocrystals. And these important modifications are summarized like multiple exciton generation in quantum dot nanocrystal, free carrier absorption, Auger recombination, etc. The essential aim of this modification is to execute more realistic efficiency calculation and to understand the fundamental physics of the devices. Here we will look at just multiple exciton generation modification in this model. Because our modification is again depending this modification, multiple exciton generation modification.
You have 5 minutes.
Sorry?
You have 5 minutes.
But I started at...
We can have a couple of questions as well.
Okay, okay, okay. Okay, when we look at a core-shell quantum dot structure, as you know, we can mention about two different type of confinement. One of them is type 1 confinement, the other one is type 2 confinement. And using these structures, for example, this is realized solar cell sample by Sargent group. And I would like to mention about multiple exciton generation. Actually, the origin of multiple exciton generation is complicated and still until debate. But the nanocrystal-based solar cell efficiency can be theoretically improved by generation of the multiple electron hole pairs from the absorption of the one photon. What is the meaning of this one? If absorbed photon energy is equal to 2 times of gap energy, this means this photon creates 2 exciton. If the photon energy equal to 3 times of the gap energy, this photon creates 3 exciton, and so on. And a multiple exciton generation has been demonstrated in quantum dot nanocrystal, such as lead sulfide, lead selenide, lead telluride, and so on. And again, as we mentioned, this external quantum efficiency in this multiple exciton generation modification, external quantum efficiency is equal to quantum yield. As we said, depending on the gap energy and incident photon energy, this quantum yield value have some integers, 1, 2, 3, and so on. And when we look at the original photogenerated current equation is this one, and this multiple exciton generation, after multiple exciton generation, this generated current is equal. This one here, quantum yield is 1. When the quantum yield is 1, there is no multiple exciton generation process. And again, this equation reduces the original Shockley-Quasar equation. And we mentioned this one. For the recombination equation, original recombination current equation is this one. After multiple exciton generation, again, there is a multiplication factor for the quantum yield here, and at the same time, exponential term in the exponential term. Okay, as a result, the original detailed balance model is modified, including multiple exciton generation. And again, the result of this modified model gives the similar results. But here we won't deal with the other situation. We will restrict ourselves just one electron hole pair situation. And as you see, this is reported for the quantum dots. But again, when we compare to result of conventional Shockley-Quasar limit, again, the graphs overlap exactly. Again, as you see, there is the material parameters is not so important. When we look at the absorption and exciton formation mechanism, as you know, if the photon energy is equal to gap energy, this photon creates an electron hole pair. If these carriers bind to each other with the exciton Coulomb potential, this is called as an exciton. If this binding is broken out, in this case, these two carriers will be free. In quantum dots, the procedure is a little different because there is a confinement, external confinement potential. So in this structure, again, the exciton is formed, but both electron and hole is confined in the same spatial region. This kind of confinement region called as type 1 region, and the recombination probability is very high. On the other hand, in type 2 structure, both electron and hole are confined different spatial region. The recombination probability is small when you compare to type 1. And this oscillator strength for this phenomena is given as this expression overlapping of the wave function, Kane energy related to materials, and exciton transition energy. And in recombination current density, recombination is an optical phenomenon, so there must be the oscillator strength in the this recombination phenomena, recombination current density. So this expression is modified by multiplication of the F. F is again oscillator strength. So as I said, this modification is just on the recombination current, because in photogenerated current, all photons energy is greater than E gap is absorbed. So there is no needing a modification. And in application of modified model by me, I used two different structures. And in these structures, I used again same core materials, indium phosphate core materials, but different shell materials, zinc sulfide and gallium phosphate. And in type 2 structure, again, the core materials are the same, but the shell materials are different. To see the effect of my modification. This is the result of conventional detailed balance model, original details balance model for the structures. Indium phosphide, zinc sulfide, and indium phosphide, gallium phosphide type 2 region. As you see, the efficiency values are the same. Again, for type 2 structure, again, the efficiency values are the same. But when we look at the modified model, the indium phosphide, zinc sulfide efficiency values is completely different, because in type 1 structure, recombination probability too much. So the current, photocurrent density will be very, very small. And as you see, maximum efficiency is about 9%. For indium phosphide, gallium phosphide structure, again, when we look at the maximum value is about 5.8. For type 2 structure, again, we can see the clearly the modified results. And also, I compared my results with the experiment. This is experimental results from ACS Nano 2015. Here, cadmium telluride, cadmium selenide quantum dots solar cell is taken. And the conventional model gives the... Okay, this is a last slide. The conventional model gives the 20.56 for the short circuit current. Open circuit voltage is 1.33 and conversion efficiency is 30.8, this value actually. Modified the model in the study. Again, short circuit current approximately the same. The open circuit voltage is 0.716 and maximum conversion efficiency is 16.60. Experimental value, when we look at the short circuit current, is this one. Experimental open circuit value is, as you see, my result is very close to this one when you compare to original detailed balance model. And again, the photo conversion efficiency is this one. And this is conclusion. Okay, I completed.
Thank you very much for your talk. And is there any question and we can have it? I think there is no question. Thank to you again. And we can move on our next speaker, Professor Hakan Tureci. The title of his speak, Machine Learning with Quantum Dynamical System. I think it's ready, Professor Tureci.
Good afternoon.
Yes, we are hearing now, and you could start, please.
1 second, let me pull up my slides to see that it would make sure it works properly.
We we are over time today. Sorry, a little bit late for you.
It's okay. 1 second. All right. Is my slide up?
Yes.
You're
Yes,
able to see it?
You could start, no problem.
Okay, thank you. Thank you very much. And good afternoon, everyone. Those online, thank you all for tuning in. I'm delighted to be part of this conference and have been enjoying the talks in my waking hours here. I hope everyone is having a wonderful time in beautiful boardroom. It's a pity I'm unable to be present there personally. So today I want to tell you about our work on a hardware-based machine learning approach. We'll be touching on foundational principles of implementing computation by using the natural time evolution of a physical system to process information. So that could be classifying images, but in this talk, I'll be talking about classifying time-dependent, to be more specific, stochastic time-dependent signals that carry information. So today's talk concerns physics of computation, computation with physical systems, and that is sprinkled with some quantum measurement theory. The people behind this work primarily are my students, Jerry Angelados and Said Khan. So this is the team. Jerry and Said and Fangjin, 3 students working on this project are right here. We can't go back to our offices yet, but we continue to carry out our work and have fun doing it virtually. So here's an overview of today's talk. The story that I will be sharing today has 2 parts. And I want to start by giving you a brief overview of the particular problem that I will be talking about. The first part of the talk is about the physics of qubit readout. This concerns a serious impediment to increasing the signal-to-noise ratio in the quantum state measurement of a superconducting qubit. Here on the left, I'm showing a superconducting qubit right here that is coupled to a transmission line resonator. And the resonator here acts as a readout cavity. And the kind of system that I'm showing here is today the basic building block of typical quantum processors. And so we'll go into this in more detail later on. But the basic idea is that one scatters off a microwave probe pulse from this resonator that houses the qubit. The state of the qubit is then imprinted onto the amplitude and phase of the microwaves scattered from this resonator. Here's a typical voltage recorded at a heterodyne detector. The red signal here is for a qubit that was in the down state before the probe pulse arrived. And the blue signal is for spin up. So the problem is the fundamental measurement noise doesn't allow you to do this instantly. Yes? And how long it takes to decide whether a qubit is up or down depends on the signal-to-noise ratio. And the speed at which one can accurately read out the state and the signal-to-noise ratio depends on the number of photons in the probe pulse that we are sending through the resonator. A simple model, the linear dispersive model on which the idea of quantum non-devolution measurement is based, would say, well, you can increase the signal to noise ratio by sending a pulse with a larger power, as shown here, yeah, and as illustrated here. But what happens as predicted by a slightly more accurate model is that the qubit now has a more complicated dynamics, and the act of measurement itself, this probe pulse, starts impacting the measured system, a phenomenon that is referred to as the quantum backaction in quantum measurement theory. Okay, so in the next, I will ask, well, can one come up with a signal processing approach that is independent of the power level and the model used to describe the readout and the particulars of the physics of readout dynamics? And one intriguing answer to that is the reservoir computing approach. Yeah, so that's the second part of my talk. Very briefly, we want to think about a superconducting preprocessor, as shown here, that does most of the job before the electronics at room temperature processes the signals. The idea of reservoir computing in this context is to feed in this raw signal that is emanating from this readout cavity containing the qubits into a dynamical system that is to be specified later on, which evolve under the scattered microwave signals and maps the state of the quantum system into the high dimensional phase space of the reservoir computer. We will then ask, can a trainable linear filter or classifier at room temperature classify the state of this quantum system? Yeah, so this is a very different approach to computing. In this case, a signal processing task with respect to von Neumann model model of computation. So in fact, this hardware-based approach points to a very general form of computing, as I will be alluding to later on. So let's go down to the details. Qubit readout is fairly standard today and is practiced almost identically in all industrial quantum computing efforts. It relies on the difference in the dispersive shift of the microwave probe pulse scattered from a resonator or transmitted through this resonator that houses the qubit that I'm showing here that is to be measured. Now, when this qubit is far detuned from the cavity resonance, the qubit in the ground state and the excited state act as slightly different resonant systems. You know, you can think of the atom as a tiny piece of dielectric whose index of refraction depends on the state of the atom. Therefore, depending on the state of the atom, the cavity resonance shown in blue is either shifted to the blue or to the red, depending on the state. As a result, when the microwave probe frequency is chosen appropriately, let's say, to be specific here, right in the middle between these two state-dependent resonances, one can, for instance, set up this the situation that the transmitted field amplitude has a phase that differs by pi, depending on whether the qubit is in the up or down state. Okay. So in practice, the accuracy of readout really depends strongly on the ability to prepare the atom either in the ground state or in the excited state with high accuracy. Okay, that's the primary thing you need to start doing this. If you know how to prepare the atom in the ground state, for instance, by a reset protocol, then you send a measurement pulse, as in here, and look at the recording of the scattered pulse at the detector. To get a typical measurement record for spin up, you send a pi pulse, as shown here, before the measurement pulse. And the two measurement recordings are shown here. And as you see, it's about 50 nanoseconds, 50 to 100 nanoseconds, through which you can start distinguishing these two signals. And repeating this measurement, you get such stochastic records that lie in these red and blue bands here. However, what I'm showing here, the data I'm showing here, this is real experimental data that's from Walraff group, is really this measurement optimized to death in an online quantum chip that is accessible through the cloud, which needs to be periodically calibrated to offset slow drifting qubit parameters. This kind of optimized readout is often difficult to attain. So in practice, the raw signal looks like this. Yeah, and what you need is you need to repeat this measurement hundreds to thousands of times, obtaining a number of samples for spin up and the number of samples for spin up, and average those records that's shown here in red dashed line and the blue dashed line. And from that, you can construct, from this average record, you can construct a matched filter, optimal linear filter for this signal processing task. And what that means is from the individual measurement record, UT, through this convolution with this optimal filter that is obtained through many measurements, you get a new signal Y for spin up and spin down, that's shown in red and blue for an individual record. And then you can construct a discrimination boundary. And if the trajectory for a particular single record falls into this red part, it's spin down. If it falls into blue part, you say it's spin up. Yeah. Okay. Now, large signal to noise ratio, SNR, can in theory be obtained by simply cranking up the power in the pulse that goes into the resonator, which would make it, this measurement process a lot faster at higher powers, as shown here. Okay, but what happens is that now this high power signal isn't anymore a probe pulse. It is actually starting to affect the qubit itself that you're trying to measure. And if you look at individual trajectories, you may end up, depending on the power, with a evolution like this, where now the qubit up state ends up showing a quantum jump to the lower state, and you have a readout, what's called a readout error. Okay, so that's a wrong classification then, and this happens more prevalently as the power is cranked up. So you could say, well, even if at high powers, the qubit dynamics is complex and difficult to predict or calculate, you don't know the precise model. Can one find a universal hardware-based approach that is model independent and independent of crosstalk that you may have in the system, that is robust and hardware efficient? We believe a hardware-based reservoir computing approach presents such a potential, and I want to tell you about our preliminary results on that. Okay. So reservoir computing is a deep learning framework for processing time-dependent data based on the idea of recurrent neural networks. If any one of you is familiar with it, but with a special training methodology. For what I want to discuss here, you can think of the reservoir computer as a continuously evolving dynamical system that responds to an input stimulus UT that is injected. So this is your reservoir computer, and converts the input to an output stream, computing a function capital F of this input data, which in turn, this function F is in turn is a functional of the output layer WO. And what is this output layer? Well, it's just a linear combination of the displacements or the states of these individual nodes of the dynamical system. So the intermediate state of the computation here is encoded in the high-dimensional phase space of this dynamical system. And you can obtain, by training, you can obtain an optimal solution for this output layer. So reservoir computing by now is well established, and the effectiveness of this approach has been demonstrated with various computational tasks, such as forecasting and classification. Don't have much time to go into it. It's a very interesting field. So here I will be discussing, you could do this just in code and software, but I'll be discussing a hardware reservoir computing approach for processing quantum signals. The reservoir computer that we envision is a device, in our case, made of Josephson nonlinear oscillators in a cryogenic environment. The input signal to be processed, this could be an arbitrary input signal, could be images, for instance, that are encoded in some way into microwave signals that are sent down this line. The signals are routed through transmission line into the fridge, exciting the network of Josephson junction oscillators and scattering off them into an output transmission line, which is then routed out of the fridge and processed in room temperature electronics. One can consider various tasks, computational tasks for such a system. In this talk, the computation task will consider classification of the quantum state of a large quantum system. I will not be talking about other things you can do. You have some parallel work where implementing image classification, pattern recognition tasks. It's quite an interesting topic, compelling. So let me get down to the specifics of how such a framework can be used to measure a large quantum system. And so in the typical setup envisioned, the quantum system we want to measure is housed in a separate, housed in the same fridge as the upstream reservoir computer. The quantum system is excited with a microwave pulse, okay? So this microwave pulse goes through the system, scatters. The typical stochastic signal, as I've shown you before, is something like this. Goes into the reservoir computer, excites the reservoir computer nodes. And these individual nonlinear oscillators, they undergo their evolution, which is also stochastic. And then the computational task done in the external software is to optimize the output layer, such that the quantum state of the measured system is classified with as high fidelity as possible. Once this is done, if you have set things up correctly, the reservoir returns the real-time probability of the measured system being in a given state. And here I want to focus on what's called joint dispersive readout of multiple qubits. So joint dispersive readout that we will focus on here allows to measure the system of multiple qubits simultaneously through a shared resonator mode. Let's for now assume that the system is described by a multi-qubit dispersive Hamiltonian and consider the case of two qubits. So we have two qubits residing in a resonator. We are scattering a pulse, getting a recording in the heterodyne detector. Let me first go over the standard implementation of joint dispersive readout using optimized filters. Okay, so first, this optimal filter approach, how it's practiced in experiments, such as has been carried out in this reference here in 2009. Just like the system before, this is initialized in known states.
You have 5 minutes.
All right. Okay, thank you. Initialized in known states with high certainty, yeah. And the measurement is performed hundreds of or thousands of times for each state. You get these measurement records, construct a match filter. You have 3 discriminating boundaries. And depending on where this measurement record falls through the match filter, you can classify the signal. In this case, it's the spin up. It's an up state. All right. So an important metric for readout calibration is classification fidelity reached on a test sample at a given time as a function of the sample size Q. Okay. So we will look at this quantity for different values of Q. So here, the filter is constructed in this record here using a single sample per state. So Q is 1, okay? And classification fidelity on a test of 500 measurements per state is plotted here. And when the peak fidelity is reached somewhere around here, fidelity is around 0.4. That means it's only about 40% of these trajectories are correctly classified. As Q's increase, the fidelity increases. And when you reach about 100 trajectories, you get an more acceptable classification fidelity. And about, this is the theoretical infinite sample size limit. And you see that even about 6 cavity lifetimes, only 95 trajectories, 95% of the trajectories are correctly classified. Even in the Q equals infinity limit, the fidelity is limited and does not ever go to 1 because the qubit decay and in experimental situations cross coupling, which is included here in the modeling. Yeah. So here I show the peak classification fidelity reach for each Q. So each sample takes about a few microseconds in practice, given that a publicly available system on the cloud needs to be calibrated periodically due to unavoidable drift in parameters, as I mentioned before. And during these periods, the system has to be offline. It's operationally important to minimize the latency involved in calibrating a readout system on publicly available hardware. So you see here that as a function of training set size Q, maximum peak classification fidelity is reached only after about 100 trajectories. And in practice, this is about 1,000 trajectories per state. Okay. So, now I will discuss the basic results from a reservoir computing approach. So here's a visualization of how training looks like for a 5-node reservoir. We have chosen the parameters to be within a range of fabrication capabilities. Here's one trajectory for one of the quadratures of the microwave signal injected into the reservoir computer. These are the trajectories conditioned on the qubit being initialized in down state at t equals 0. Yeah. Over the time scale of several cavity lifetimes, the classification reaches a quasi-steady state, as you see here, and this trajectory is classified as 1-1. And the ground truth is shown for 1-1 state up here. You see that despite the fact that the qubit, due to back action, one of the states is actually flipped, the reservoir still is able to classify this trajectory correctly, because what we want to do is really classify the initial state of the system before the microwave pulse. Details aside, the most striking result of this work and the takeaway message is that the reservoir computer is a fast learner. Already after a few samples, the reservoir is able to classify with rather high fidelity. As the number of training samples increases, the peak classification fidelity basically reaches its peak already at a few samples and remains fairly constant, as you see in this blue plot here. And I want to remind you that this is a small reservoir, just 5 nodes. Striking to compare this with match filter, which requires a substantial number of training samples to reach a peak classification fidelity that's satisfactory for practical applications. So, of course, as physicists, we are intrigued how this is possible at all. And there's one can actually get physical insight into the effectiveness of the reservoir in learning fast. But I think I'm out of time here to discuss that part, so I will just point out here that nonlinearity turns out to be essential for successful robust classification. A linear reservoir fails to do the job. So these can be read in our recent preprint that I put up if you're interested. So I will jump to the conclusions. Reservoir computing approach that I've discussed today to quantum signal processing appears to be a hardware efficient approach for cryogenic analog processing of systems, quantum systems, especially large quantum systems. Reservoir computing turns out to have a very fast learning capacity and is especially well suited for more complex measurement tasks that are based on repeated readout like quantum state tomography. And this kind of paradigm is really generalizable to various quantum systems and measurement schemes, both in microwave and optics. All right. This is the end of my presentation. Thank you all for listening. I wish you a good time in Bodrum.
Thank you very much, Professor Tureci. And if is there any question we can ask? And there is no question. And thank you, Professor Tureci, again. I am closing this section. Hope you will enjoy poster section at 2 o'clock. Okay, bye-bye.